Hello, and welcome to Learn When You Sleep, where curiosity finds the shape of a quiet breath, and the grandest questions that science can ask become companions for the night. Tonight, we are going to do something that no human being has ever done in the ordinary course of living. We are going to think forward. Not forward by a year, not forward by a century, not even forward by 1,000,000 years. Though 1,000,000 years is already so far beyond daily experience that it might as well be another universe entirely. Tonight we are going to think forward across timescales so immense, so far beyond the reach of ordinary language, that the very words we use to describe time will begin to feel insufficient, and new ones will have to quietly take their place. The subject of tonight's journey is the long future of the universe itself, not the future of a country or a civilization or even a species, but the future of everything. Of all the stars that have ever burned and all the stars that are yet to burn, of all the galaxies drifting through the dark, of all the matter and energy that exists in any form anywhere across the observable cosmos. We are going to follow all of it, step by slow step, through eras so vast that the present moment, with all its light and warmth and noise and activity, will come to seem like the very first syllable of a story that takes an almost incomprehensible length of time to reach its final, quiet, fading page. Before we begin, I want you to take a moment to settle in. Feel the weight of your body against whatever surface is holding you right now. Notice the temperature of the air around you, cool or warm, the small sounds of the room, the rhythm of your own breathing. You are here, right now, in this moment, on a small and beautiful planet orbiting a middle-aged star in a galaxy that is, by the standards of what we are about to discuss, extraordinarily young and slashingly alive with light. That is where we are standing as this journey begins. That is the shore from which we will push off. Now, the long future of the universe is not a frightening subject, even though it involves the gradual dimming of almost everything we know. It is not a story of sudden catastrophe or violent collapse. It is not an ending in the dramatic sense that the word ending usually implies. It is something far more subtle than that, and in its own way far more beautiful. The universe does not go out like a flame pinched between two fingers. It fades slowly, patiently, over stretches of time so long that the distance between the birth of the first stars and the death of the last ones is, compared to what comes after, barely a flicker. It grows quieter the way a great fire grows quieter after the wood has been spent, not extinguished in a single breath, but cooling gradually, ember by ember, the last warmth lingering in the dark long after the last light has gone. Tonight, we will follow that cooling. We will walk through 5 great eras that astronomers have described when they turn their equations and their imaginations toward the deep future. We will begin in the era we already live in, the Stelliferous Era, the age of stars, where the cosmos burns with the light of hundreds of billions of suns scattered across hundreds of billions of galaxies. We will pass through the slow decline of that age, through the gradual exhaustion of the gas that feeds new stars, through the long twilight of the smallest and most patient stars, which will burn so dimly and so slowly that they will outlast everything else in the visible universe by trillions upon trillions of years. Then we will enter the Degenerate Era, the age of cooling remnants, where the universe is populated not by burning stars but by their ghosts. White dwarfs, slowly radiating the last of their heat into a space that grows ever colder. Neutron stars, spinning in silence, no longer pulsing with the radio signals that once let us detect them from billions of light years away. The Degenerate Era is a quieter universe, a darker universe, but still a universe with structure, still a universe where matter exists in organized, recognizable forms. After that comes the black hole era, the age in which the dominant objects in the cosmos are the most extreme things that physics allows. Black holes, formed from the deaths of massive stars and from the collapse of entire galaxies, will be the last large structures remaining, and even they will not last forever. They will dissolve slowly through a process called Hawking radiation, leaking energy into the surrounding space one quantum at a time, growing smaller over unimaginably long stretches of time, until even the largest of them finally evaporates completely, releasing one last quiet burst of energy into a universe that is otherwise almost entirely dark and cold. And then, at last, we arrive at the dark era, the age in which even the remnants of the remnants have faded. The age in which the universe is populated by nothing more than isolated subatomic particles drifting through an expanding void, separated by distances so enormous that interaction between them becomes vanishingly rare. The dark era is not quite the end, because physics is not certain that it has a final ending to offer, but it is the closest thing to silence that the universe will ever reach. All of this lies ahead. And tonight, we will visit each of these eras in turn, taking our time, letting each one settle in the way that a long and slow piece of music settles, not rushing toward the final note, but resting in each passage as it comes. So how do we think about something like this? How do we hold in our minds a span of time so enormous that every human life ever lived, every civilization that has ever risen and fallen, every species that has ever walked or swum or flown on this planet, would fit inside it not once but millions of times over, without even making a visible dent in the total? The honest answer is that we cannot think about it directly. Our minds were not built for this. They were built for seasons and years, for tracking the movements of animals and the ripening of fruit, for remembering the faces of family and the paths through familiar forests. They were not built to feel the weight of 100 trillion years, but here is the remarkable thing. We do not need to feel the weight of it to understand it. And this is one of the quietest but most powerful gifts that mathematics and physics have given us. We can reason about timescales we cannot feel. We can follow the logic of physical laws to conclusions that no conscious being will ever witness. We can describe with genuine confidence what the universe will be doing in 10 billion years, or 100 trillion years, or timescales so far beyond even those that writing the numbers requires a special notation called scientific notation, in which the exponent, the small raised number that tells you how many zeros to add, does more work than the number itself. This ability to reason beyond experience is not unique to cosmology. Mathematicians work with infinities they will never count. Geologists describe processes that unfold over millions of years without having observed them. Evolutionary biologists trace lineages across hundreds of millions of years of change. In each case, the human mind is doing something extraordinary. It is extending its reach far beyond the boundaries of direct experience, using logic and evidence and the deep consistency of natural law to illuminate places it could never physically go. For the future of the universe, the foundation of all this reasoning is physics. The laws of thermodynamics, which describe how energy flows and how disorder tends to increase over time. The laws of nuclear physics, which describe how long stars can burn and what happens when they stop. The principles of quantum mechanics, which govern the behavior of the very smallest particles and which lead, through a strange and beautiful chain of reasoning, to the conclusion that even black holes must eventually dissolve. and the cosmological equations that describe how space itself is expanding, carrying everything within it into an ever larger, ever colder, ever more dilute arrangement. These laws do not change over time. They are not different in the far future than they are today. And so the story they tell about what the universe will eventually become is not a guess or a fantasy. It is the most honest and rigorous answer that science can currently give to the question of what lies ahead. I want you to know before we go further that none of what we will discuss tonight needs to feel sad. The long future of the universe is, in one very real sense, the most reassuring story that science has to tell. It tells us that the universe is patient beyond all imagining. It tells us that even after every star has gone out, something will still exist. It tells us that the laws of physics, which gave us light and warmth and the possibility of life, do not simply abandon the universe when the fuel runs low. They keep working, keep shaping, keep governing, long after the last sun has faded. And it tells us something else, something quieter and perhaps more important. It tells us that right now, in this era, in this age of stars, we are living in one of the most remarkable and most fleeting chapters of the entire cosmic story. We are here at the bright beginning, and that, when you really hold it in your mind, is a kind of gift. So take a breath, let your body rest, and let us begin the long journey forward through all the ages that the universe has yet to live, from the last burning stars to the final silence of deep time. Before we travel forward into the deep future of the universe, it is worth pausing here at the threshold and asking a question that might seem simple but turns out to be surprisingly rich. What does it actually mean to think about the future? Not the near future, not the future of a human life or a civilization, but the future of the cosmos itself, across timescales that dwarf the current age of the universe by factors so extreme that ordinary language simply has no framework to contain them. When we imagine the future in daily life, we think in hours and days. We picture next week, or next year, or perhaps the next several decades if we are thinking about retirement or the lives of our children. The boldest long-term planners among us might occasionally stretch their thinking to a century, imagining what a city will look like in 100 years, or what the climate will be doing, or what technologies might exist. Even the grandest human institutions, the oldest religions, the most ancient traditions, operate on timescales of a few thousand years at most. 1,000 years ago, the Norman conquest of England had just taken place. 10,000 years ago, agriculture was just beginning to emerge. 100,000 years ago, modern humans had barely spread beyond Africa. These numbers already feel vast and remote. And yet, compared to the timescales we will be visiting tonight, 100,000 years is nothing. It is not even a rounding error. It is smaller than a single step on a staircase that climbs for trillions of years. And the staircase itself, the full span of the universe's future that we will be discussing, is so tall that the mind flinches when asked to look all the way to the top. There is something deeply human about asking that question. Every culture in history has wondered what will become of the world. Every tradition has its own stories about endings and renewals, about final ages and golden eras, about the last day or the last fire or the return of light after darkness. These stories come from the same impulse that drives cosmologists to their equations, the desire to know. The hunger to understand not just where we came from and what we are, but where all of this is going, and what it will look like when it gets there. Tonight, we are going to follow that impulse as far as science currently allows. We will not find comfort in mythology or in the reassurance of cycles that return everything to its beginning. The universe that physics describes does not return. It moves forward, always in the direction of greater age and greater stillness. But there is comfort in that picture too if you sit with it long enough. The universe is not going somewhere violent or sudden. It is going somewhere quiet. It is moving, step by enormous step, toward a kind of peace that no word in any human language was ever designed to describe. And we are here, right now, in the noisiest and brightest and most energetic moment of that journey. We are the morning of the day. We are the first page of the book. To think about the future of the universe is to realize, with a strange and gentle shock, just how early we are, just how much story remains to be told, and just how fortunate we are to be alive in this chapter when the universe still has so much light to offer. Let that thought settle for a moment. You are not living at the end of something. You are living at the very beginning of something so long and so slow, and so far beyond the reach of ordinary imagination that the end of it is effectively unreachable in any practical sense. The universe has barely started. The stars are still young. The fire is still burning. And we are here to see it, which is more than any living thing will be able to say for most of the time that lies ahead. That is not a small thing. That is, in fact, one of the most remarkable things that could be true of any conscious being in the entire history of the cosmos. So let us go forward together slowly, without rushing, one era at a time. Let us look at what is coming, not with dread, but with the same quiet wonder that makes us look up at the night sky in the first place. The future of the universe is long, and it is strange, and it is, in its own deep way, beautiful. To truly appreciate where the universe is going, it helps first to appreciate, with some care and some slowness, where it is right now. Not in the abstract sense of knowing that it is 13.8 billion years old and contains some large number of galaxies, but in the more intimate sense of feeling what kind of universe this actually is, what it is doing, what it is full of, and why that fullness is, from the perspective of deep time, something close to miraculous. We live in what astronomers call the Stelliferous Era. The name comes from Latin, from the words for star and for bearing or carrying, and it means simply the age that carries stars. The Stelliferous Era is the current epoch of the universe, the age in which stars exist as the dominant feature of the cosmic landscape. And when you take in the scale of what that means, when you really pause and let it unfold in your mind, it is an almost overwhelming picture of abundance. Consider what a star actually is for a moment. A star is a sphere of gas, mostly hydrogen, so massive that its own gravity compresses its core to temperatures of millions of degrees, hot enough and dense enough that hydrogen nuclei are forced together to form helium, releasing in the process an enormous amount of energy. That energy pushes outward against gravity, and the balance between the two forces, gravity pulling inward and radiation pressure pushing outward, is what keeps a star stable, what keeps it from either collapsing into itself or flying apart. A star is, in the most literal sense, a controlled nuclear explosion lasting billions of years. And the universe right now is full of them. How full? Our own galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. That range is already beyond comfortable visualization. If you counted one star per second without stopping, counting 400 billion stars would take roughly 12,000 years. And the Milky Way is just one galaxy. The observable universe contains an estimated 2 trillion galaxies. Each of those galaxies contains its own population of stars, ranging from a few million in the smallest dwarf galaxies to several trillion in the largest giant ellipticals. The total number of stars currently burning in the observable universe is estimated to be around 1 followed by 24 zeros. 1 septillion stars, all of them burning, all of them producing light and heat, and the heavy elements that make planets and chemistry and life possible. This is the universe as it currently stands, a cosmos ablaze with nuclear fire, threaded through with the light of more suns than there are grains of sand on all the beaches of Earth. It is a universe in which every direction you look from any vantage point contains light, contains warmth, contains the signatures of active, ongoing, energetic processes. Stars are being born right now in clouds of gas and dust scattered across countless galaxies. Stars are dying right now in brilliant supernovae that scatter the atoms of carbon and oxygen and iron across the surrounding space, enriching the next generation of worlds. Planets are forming in the disks of debris around young stars. And somewhere in all of that, at least once that we know of, the chemistry of life has found a foothold. Our own sun is a particularly useful reference point for understanding where we are in cosmic time. The sun formed approximately 4.6 billion years ago, roughly a third of the way through the current age of the universe. It is a middle-aged star, a yellow dwarf of a type called G-type, comfortably ordinary by cosmic standards, neither the most massive nor the least, neither the shortest-lived nor the most enduring. It has been burning steadily for 4.5 billion years, and current models suggest it has approximately 5 billion years of hydrogen fuel left in its core before it will begin to change in significant ways. 5 billion years of remaining sunlight. That number is worth sitting with for a moment, because it illustrates just how much time remains even in the relatively near-term future by cosmic standards. 5 billion years from now, the sun will still be burning. The Earth, or what remains of it, will still be orbiting it, though likely in a very different condition than it is today. The universe will still be in the Stelliferous Era, still full of stars, still producing light and warmth, still very much alive by the standards of what is to come. But the Stelliferous Era is not permanent. Nothing about the universe is permanent, and that is one of the central truths that tonight's journey is built around. The abundance we see right now is the product of a specific set of conditions that existed in the early universe, conditions that allowed vast clouds of hydrogen and helium to collapse into stars, and that set in motion the cycles of stellar birth and death that have been enriching the cosmos for billions of years. Those conditions are slowly changing. The gas that feeds star formation is slowly being used up. The rate at which new stars are being born has been declining for billions of years already, and it will continue to decline. We are not at the peak of the Stelliferous Era. We are past it. The peak of star formation in the universe occurred roughly 10 billion years ago, when galaxies were younger and gassier and more collisional, when the raw materials for new stars were more abundant and more easily triggered into collapse. Since that peak, the rate of star formation across the observable universe has been falling steadily, like the output of a factory that is slowly running low on raw materials. The factory is still running. Stars are still being born today, but fewer and fewer with each passing billion years. This is not a crisis. It is simply the natural consequence of a finite supply of star-forming gas in a universe that has been turning that gas into stars for nearly 14 billion years. The universe is not running out of stars suddenly. It is running low on the fuel to make new ones, gradually, over timescales that dwarf the entire current age of the cosmos. The Stelliferous Era still has roughly 100 trillion years ahead of it, and within that span, there will still be stars burning for most of that time, still be planets orbiting them, still be chemistry happening in the warm zones around glowing suns. But it is important to feel, as we begin this journey, what we are leaving behind. The universe as it currently exists, this blazing, busy, star-forming cosmos full of light and heat and complexity, is not the default state of the universe. It is a phase, a remarkably beautiful and fertile phase, but a phase nonetheless. It emerged from the hot, dense simplicity of the Big Bang, built itself up through billions of years of star formation and galactic evolution, reached its peak of luminous activity roughly 10 billion years ago, and has been in a gradual, very slow decline ever since. We are in that decline right now, though you would never know it by looking up. The sky still looks full of stars because, for all practical purposes, it is. The decline is too slow, too gradual, too spread across too vast a timescale for any observer in the current era to perceive it directly. It is like standing on a beach and trying to see the tide going out by watching for a single minute. The change is real, but it is happening on a scale that requires the patience of geological time to notice. Tonight, we are going to borrow that patience. We are going to let time pass in our imagination, far faster than it passes in reality, and we are going to watch what happens. We are going to watch the Stelliferous Era wind slowly down, watch the last new stars form and burn and die, watch the universe transition into something quieter and stranger, and in its own way, no less worthy of our wonder. But before we go there, let us rest here for just a little longer in the richness of the present. Let us feel, without rushing, what it means to live in a universe that is still full of burning stars, still producing the light and heat that make worlds like ours possible, still in the morning of its long and patient life. The fire is still burning. The stars are still there. And for now, at least, the night sky is full of them. Now that we have a sense of where we are, standing in the bright and busy middle of the Stelliferous Era, it is time to understand this age more fully. Because to understand where the universe is going, you first need to understand what a star really is, how it lives, how it dies, and what it leaves behind. Stars are not simply points of light in the night sky. They are the engines of the universe during this era, the machines that process raw hydrogen into heavier elements, that generate the light and heat that make chemistry and complexity possible, that set in motion the whole chain of events that leads eventually to planets and oceans and living things that can look up and wonder about the sky above them. The story of a star begins long before the star itself exists. It begins in a cloud. Not a cloud in the ordinary sense of fluffy white formations drifting across a summer sky, but a nebula, a vast region of gas and dust spread across dozens or even hundreds of light years of space. These clouds are mostly hydrogen, the simplest and most abundant element in the universe, left over from the Big Bang and recycled by previous generations of stars through the violence of supernova explosions and the gentle exhalations of dying suns. They are cold by stellar standards, only a few tens of degrees above absolute zero, and they are extraordinarily thin by any terrestrial standard. A cubic meter of a typical molecular cloud contains fewer molecules than the best vacuum that human technology can produce in a laboratory on Earth. And yet these thin, cold, vast clouds are where stars come from. Given enough time and given some triggering event, perhaps the shockwave from a nearby supernova, perhaps the gravitational disturbance of a passing galaxy, perhaps simply the slow accumulation of self-gravity as the cloud drifts through space, parts of the cloud begin to collapse. A dense knot forms within the larger cloud. Gravity pulls surrounding gas inward, accelerating the collapse, raising the temperature and pressure at the center. The collapsing knot begins to rotate, forming a flattened disk of material around a central concentration that grows ever denser and ever hotter. After thousands of years of collapse, the central concentration reaches temperatures of around 10 million degrees Kelvin. At that temperature, with hydrogen nuclei packed tightly enough together by the enormous pressure of the surrounding gas, nuclear fusion ignites. Hydrogen nuclei, which are simply protons, begin to collide and fuse together, forming helium nuclei and releasing energy in the process. That energy, flowing outward as radiation and pressure, pushes back against the continuing collapse of gravity. A balance is struck. The collapsing cloud has become a star. This process, from the initial collapse of a gas cloud to the ignition of a new star, typically takes somewhere between 100,000 and 1 million years, depending on the mass of the forming star. Massive stars form quickly and burn brightly. Small stars form more slowly and burn dimly. But the outcome is the same. A sphere of plasma in hydrostatic equilibrium, its inward gravity balanced by the outward pressure of nuclear energy, burning steadily in the darkness of space. Once a star is born and settled into this stable balance, it enters what astronomers call the main sequence, the long, steady phase of hydrogen burning that defines the bulk of most stars' lives. Our own sun has been on the main sequence for about 4.5 billion years, and will remain there for approximately 5 billion more. During this time, it will shine with a nearly constant luminosity, losing mass slowly through the solar wind, gradually warming as the helium ash of fusion accumulates in its core and causes the core to contract and the outer layers to expand slightly. But for all practical purposes, the sun we see today is essentially the sun that shone on the first dinosaurs, and the sun that will shine on whatever forms of life inhabit this planet a billion years from now. The length of a star's main sequence lifetime depends almost entirely on its mass, and here the universe reveals one of its most counterintuitive rules. The more massive a star is, the shorter its life. You might expect the opposite. A more massive star has more fuel, but it also has far more gravity pressing down on its core, which means it needs to generate far more energy to hold itself up, which means it burns its fuel at an enormously higher rate. A star 10 times the mass of the sun burns roughly 10,000 times as much fuel per second, and consequently lives for only about 10 million years, compared to the sun's 10 billion year lifespan. Stars that are 50 or 100 times the mass of the sun may exhaust their hydrogen cores in only a few million years, blazing for their brief time as luminous blue giants before dying in spectacular supernova explosions. At the other end of the scale, small stars live for an almost incomprehensible length of time. Stars with about half the mass of the sun have main sequence lifetimes of tens of billions of years. Stars with a quarter the mass of the sun have lifetimes measured in hundreds of billions of years. And at the very bottom of the stellar mass scale, the dimmest and smallest stars that can still sustain fusion, stars with roughly 8% of the sun's mass, have theoretical lifetimes stretching into the trillions of years. These are the red dwarfs, and they will become the dominant feature of the Stelliferous Era as it moves toward its long twilight. The variety of stars in the universe right now is one of the things that makes this era so rich. At one extreme, you have brilliant blue giants, burning with a ferocity that will exhaust them in mere millions of years, making them cosmically speaking extremely brief candles. At the other extreme, you have dim red dwarfs, glowing with such frugal restraint that they will still be burning long after everything else in the Stelliferous Era has gone dark. In between, you have the whole spectrum: orange dwarfs, yellow dwarfs like the Sun, and yellow-white stars, each with its own characteristic temperature, luminosity, and lifespan. Right now, all of these types exist simultaneously. Open any astronomical catalog and you will find stars of all masses and all ages, from newly formed protostars still embedded in their birth clouds to ancient red giants in their final throes, scattered together across the sky in a rich mosaic of stellar evolution. The universe right now is not a uniform place. It is diverse, varied, textured with the full range of stellar life at every stage. When a star finishes its main sequence life, the path it takes depends once again on its mass. Low-mass stars like the Sun, which make up the vast majority of all stars, end their lives in a relatively gentle way. As hydrogen is exhausted in the core contracts and heats up, causing the outer layers of the star to expand enormously. The star swells into a red giant, its outer atmosphere puffing outward to perhaps 100 times its original radius. In the case of the Sun, this expansion will eventually engulf the inner planets of the solar system, including the Earth. The gentle warmth of a middle-aged star will become the scorching interior of an expanding red giant's atmosphere. Eventually, the outer layers of the red giant are ejected altogether, drifting away into space as a beautiful, glowing shell of gas called a planetary nebula. These are among the most visually stunning objects in the sky: luminous rings and bubbles and hourglasses of ionized gas, lit from within by the hot stellar remnant at their center. The ejected material is returned to the interstellar medium, enriched with carbon and nitrogen and other elements forged during the star's life, available to be incorporated into the next generation of stars and planets. What is left behind at the center of the planetary nebula is a white dwarf, a small, dense, incredibly hot object composed mostly of carbon and oxygen, the ash of the star's nuclear burning, with no more fuel to burn and no more nuclear reactions to sustain it. A white dwarf is simply a glowing remnant, slowly cooling over billions of years, gradually fading from white to yellow to orange to red to, eventually, the ultimate cold darkness of a black dwarf. We will return to white dwarfs later in our journey, because they play a central role in the next great era of the universe's future. Massive stars end their lives far more dramatically. After exhausting their hydrogen, they continue burning through heavier and heavier elements, from helium to carbon to neon to oxygen to silicon, each successive fuel stage burning faster and hotter than the last. Eventually, the core of the star consists primarily of iron, which cannot be fused to release energy because iron is the most tightly bound of all atomic nuclei. At that point, the core collapses in less than a second, triggering a catastrophic explosion called a core collapse supernova. The outer layers of the star are blasted into space at a significant fraction of the speed of light, creating a shockwave that can sweep through entire regions of a galaxy, compressing gas clouds and triggering new rounds of star formation. The energy released in a single supernova can briefly outshine an entire galaxy. What remains after the supernova depends on the mass of the original star. If the star was not too massive, the collapsed core becomes a neutron star, an object roughly the size of a city but containing 1.5 to 2 times the mass of the Sun, so dense that a teaspoon of its material would weigh about 100 million tons on Earth. If the original star was very massive, even the neutron star is not stable, and the core continues collapsing until it forms a black hole, a region of spacetime where gravity is so strong that not even light can escape. All of these processes are happening right now throughout the universe. Stars are being born in nebulae. Stars are living out their long main sequence lives. Stars are dying as planetary nebulae and white dwarfs, as supernovae and neutron stars, as the seeds of black holes. The Stelliferous Era is not a static tableau. It is an ongoing drama, a continuous cycle of birth and death and recycling, driven by the simple and ancient force of gravity and the nuclear fires it kindles. And it is in this context, this rich and varied and active context, that we need to understand what will happen as the era winds down. The diversity and activity of the current universe is not a permanent condition. It is the product of an abundant supply of hydrogen and a favorable set of initial conditions. As those conditions change, as the gas supply dwindles and the most massive and most brilliant stars exhaust themselves and die, the universe will settle into something simpler and quieter. But before it does, there will be one last great chapter in the Stelliferous Era, the age of the red dwarfs, when the smallest and most patient stars finally get to dominate the sky. If you were to ask what the most common type of star in the universe is, the answer might surprise you. It is not a star like the Sun. It is not a brilliant blue giant or a golden yellow dwarf. The most common stars in the observable universe are red dwarfs, dim and cool and small, burning with such frugal economy that most of them are completely invisible to the naked eye, even though some of them are among the closest stars to Earth. And in the long twilight of the Stelliferous Era, it is these unassuming little stars that will be the last ones left burning. It is they who will define the final chapter of the age of stars. To understand what red dwarfs are, it helps to picture the Sun and then imagine shrinking it. A red dwarf is a star with roughly 8 to 50% of the Sun's mass. At the lower end of that range, the star is barely massive enough to sustain nuclear fusion at all. Its core temperature is low by stellar standards, only just hot enough to force hydrogen nuclei together. As a result, it burns its fuel with extraordinary patience, fusing hydrogen at a rate so slow that its total energy output is a tiny fraction of the Sun's. The faintest red dwarfs glow with only about 1/10,000th of the Sun's luminosity, which is why they are so difficult to see from a distance despite being so numerous. The nearest star to the Sun, Proxima Centauri, is a red dwarf. It is only 4.2 light-years away, practically a next-door neighbor in cosmic terms, and yet it is completely invisible to the naked eye. You could stare at the patch of sky where it sits and see nothing, because it shines with less than 2/1000ths of the Sun's brightness. Its surface temperature is around 3000 Kelvin, compared to the Sun's nearly 6000 Kelvin, which is why it glows red rather than yellow or white. It is the color of a dying ember rather than the color of a full flame. And yet Proxima Centauri will outlive the Sun by a margin that makes the Sun's lifespan seem brief. The Sun has an expected total main sequence lifetime of about 10 billion years. Proxima Centauri has a theoretical lifespan of approximately 4 trillion years. That is 4,000 billion years, compared to the Sun's 10 billion. It will still be burning long after every Sun-like star in the observable universe has exhausted its fuel and collapsed into a cooling white dwarf. In the context of the Stelliferous Era, which will last roughly 100 trillion years in total. The Sun is a brief flare and Proxima Centauri is a long, slow, patient candle. There are several reasons for this extraordinary longevity. The first, as we discussed, is that small stars burn their fuel at a much lower rate per unit of mass. But there is a second reason that is perhaps even more significant. Red dwarfs are what astronomers call fully convective. This means that the material inside them is constantly circulating, like a pot of soup slowly stirring itself on a gentle heat. In the Sun and in larger stars, convection only occurs in certain layers, while the core remains relatively isolated from the outer layers. This means that a large star uses only the hydrogen in its core, and when that is exhausted, the star begins to die even though there is still hydrogen elsewhere in its interior that it cannot access. In a red dwarf, by contrast, the constant circulation ensures that all of the hydrogen throughout the star is gradually brought into the core and used as fuel. A red dwarf is therefore able to burn nearly all of its hydrogen, not just the fraction in its core. It is as if a car engine that could only access the fuel in one small section of the tank were suddenly upgraded to access the entire tank. The result is not just a longer life, but a dramatically longer life. The red dwarf essentially burns itself almost completely, converting the vast majority of its hydrogen into helium before it finally begins to change. What happens when a red dwarf eventually exhausts its fuel is different from what happens to a sun-like star. Because of their lower masses and lower core temperatures, red dwarfs do not have the conditions needed to ignite helium burning after the hydrogen is gone. They do not swell into red giants and eject planetary nebulae. Instead, they simply become hotter and brighter as the hydrogen runs low, eventually becoming what astronomers call a blue dwarf, a small and intensely hot object that shines blue-white for a brief period before contracting into a cold, dark remnant. Interestingly, no blue dwarfs have ever been observed because the universe is not old enough yet for any red dwarf to have exhausted its hydrogen supply. The youngest stars in the universe, the red dwarfs, are all still in the early or middle stages of their lives. Even the oldest red dwarfs that formed shortly after the Big Bang are only about 13 billion years old, which is still a tiny fraction of their total lifespans. The universe has not yet seen a red dwarf die. All of them are still burning. As the Stelliferous Era continues and the larger stars exhaust themselves, this will increasingly be the defining fact of the universe. Imagine the sky several trillion years from now. The brilliant blue giants are long gone, their lifetimes measured in millions of years now ancient history. The sun-like stars, the G-type yellow dwarfs and the somewhat smaller orange dwarfs, have mostly exhausted their fuel and left behind white dwarfs. Even the slightly smaller K-type stars have faded. What remains burning in the sky is mostly red dwarfs, and there are a great many of them. Current estimates suggest that red dwarfs make up somewhere between 70 and 80% of all stars in the Milky Way. In the observable universe, the fraction is similar. Most stars, by number, are already red dwarfs. They are simply too faint to dominate the current appearance of the sky, which is lit up by the much rarer but much more luminous massive stars. But in terms of sheer count, the universe is already a red dwarf universe. It just does not look like it yet. As the Stelliferous Era winds down over the coming trillions of years, this numerical dominance will become an actual visual dominance. Galaxies will gradually lose their bright blue arms, those regions of active star formation lit by massive young stars, because new stars will form less and less frequently as the gas supply runs low. The brilliant supernovae will become rarer and then rarer still. The universe will grow dimmer, not suddenly or dramatically, but by steady degrees, as each generation of massive and medium-sized stars exhausts itself and leaves behind only a cooling remnant. But through all of this dimming, the red dwarfs will persist. They will be the last holdouts. While everything else is fading, they will continue their slow, patient burning, their cool red light the only glow remaining in a universe that was once blazing with the light of a septillion suns. If you could stand on a planet orbiting a red dwarf several trillion years from now, you would look up at a night sky almost entirely empty of stars. Most of the white dwarfs would be too dim to see at great distances. The stellar remnants would be dark and cold, but your own sun, that little red ember, would still be burning, still providing warmth, still making chemistry possible, still, in some sense, holding a tiny candle against the enormous dark. There is something deeply poignant about this image. The red dwarfs are, in most ways, the humblest of all stars. They are the dimmest, the coolest, the least dramatic. No brilliant supernova will end their lives. No spectacular red giant phase will briefly illuminate their surrounding space. They will simply burn and burn and burn with extraordinary patience, outlasting everything around them by trillions of years, the last survivors of the age of stars. And when they too finally exhaust their fuel and cool into dark remnants, the Stelliferous Era will be truly over. The transition from the Stelliferous Era to what comes next will not be a sudden event. It will be a gradual fading, like the last light of evening giving way to full night. As the final red dwarfs run low on hydrogen, they will brighten briefly as blue dwarfs before contracting and cooling. One by one, across a span of time stretching over trillions of years, they will go dark, and the universe will enter the next great era of its history, an era not of burning stars but of the cold, compressed ghosts they leave behind. That transition is what we will explore next. But before we go there, let us stay here for a moment in the long twilight of the red dwarfs. Let us imagine those countless small stars glowing quietly in the dark, each one a tiny flame of patient nuclear fire, each one outliving by vast margins every other kind of star the universe ever made. They are not the brightest stars. They are not the most dramatic, but they are the most enduring. And in that endurance there is a kind of quiet grandeur. The last stars burning will be the smallest ones. The universe will end its stellar age not with a bang, but with the slow, steady glow of the most modest fires it ever kindled. There will come a moment, somewhere in the vast stretch of time between now and 100 trillion years from now, when a star is born for the very last time. A cloud of gas will collapse, a core will ignite, a new sun will flicker into being in the darkness of a universe that has grown very old and very quiet. And that star will be the last one. After it, no more stars will form. The age of stellar birth will be over. The universe will still have stars in it for a while, but they will be the last generation, burning down slowly, and when they are gone, they will not be replaced. We do not know exactly when this will happen. It depends on factors that are difficult to calculate precisely, on how much star-forming gas remains in galaxies at various points in the future, on whether the small dwarf galaxies that orbit larger ones eventually merge and trigger new bursts of star formation, on the fine details of how red dwarfs cycle their material, and whether any of it escapes back into the interstellar medium to seed new generations. But the rough timescale is clear enough. The last star formation events will occur somewhere in the range of 100 trillion years from now, which is roughly 10,000 times the current age of the universe. To really feel what that means, it helps to think about what the universe will look like in the lead up to that final birth. Long before the very last star forms, the universe will already look dramatically different from the way it looks today. The decline of star formation has been gradual, but over many trillions of years, the cumulative effect is profound. The brilliant spiral galaxies we see today, with their luminous arms traced by hot young stars and glowing nebulae, will be long gone. Most of the gas that currently fills the spiral arms of galaxies will have been processed through stars already, converted into heavier elements, locked into stellar remnants. The galaxies themselves will have changed shape, many of them having merged with neighbors over the intervening trillions of years, their spiral structures long since smoothed out into the more rounded forms of elliptical galaxies. The sky will be darker. Not dark in the way that a city sky on an overcast night is dark, where the absence of stars is a local obstruction. Dark in a more fundamental way, the way a forest looks dark after most of the trees have been felled, and only a few scattered ones remain. The stars that do still burn will be mostly red dwarfs, those dim and patient little suns, glowing far too faintly to illuminate their surroundings in any meaningful way. Between them will stretch unimaginable distances of empty space, and the white dwarfs and neutron stars and black holes left behind by earlier generations of stars will contribute little or no visible light. The interstellar medium, the gas and dust that fills the space between stars within galaxies, will be mostly exhausted. The great molecular clouds that today serve as stellar nurseries, those dense, cold regions where gravity slowly builds up enough material to ignite new suns, will be depleted. Some gas will still exist, return to space through the gentle stellar winds of dying red dwarfs, and through the material ejected in the occasional event when a white dwarf accumulates enough mass from a companion to trigger a thermonuclear explosion. But the density of this material will be vastly lower than it is today, and the conditions needed to collapse it into a new star will become increasingly rare. In some ways, the last phases of star formation in a galaxy will resemble the last embers of a fire that has been burning for an enormous length of time. Most of the wood is gone. The main blaze died out trillions of years ago. What remains is scattered, small, and diminishing. Occasionally, a pocket of gas will still be dense enough and cold enough to collapse, and a red dwarf will flicker into existence. But these events will be separated by longer and longer intervals, happening less and less frequently, until finally, a last collapsing cloud forms a last star. What might that last star be like? Almost certainly, it will be a red dwarf. The conditions that favor the formation of very massive stars require large amounts of dense gas coming together quickly, and by the far future of the Stelliferous Era, those conditions will no longer exist. The last star will likely be small, dim, and cool, a modest little object that will then proceed to burn for trillions of years more before finally exhausting its hydrogen and fading. It will have no audience. No civilization capable of observing it will exist at that point, at least not as far as we can currently imagine. It will simply form and burn in the dark, the final spark of the age of stars, unwitnessed and unhurried. But even after the last star forms, the Stelliferous Era will not immediately be over. The red dwarfs already burning when the last new one is born will continue to burn for trillions of years afterward. Remember that a red dwarf with half the mass of the Sun has a theoretical lifespan of roughly 80 billion years. A red dwarf with only a tenth of the Sun's mass might burn for 10 trillion years or more. So the last stars to form will burn long after any new ones are possible, and the red dwarfs already burning will outlast them in turn. The end of the Stelliferous Era is therefore not a moment but a process, a slow fade that unfolds over trillions of years. It is not the death of the last star that ends the era. It is more accurate to say that the era ends when the conditions for stellar life no longer exist in any meaningful way, when the universe has moved so far beyond the age of abundant gas and active star formation that what remains is only the slow cooling of the last embers. There is something deeply philosophical about this picture. The Stelliferous Era has given the universe everything that we associate with the cosmos: light, heat, elements, chemistry, the possibility of planets and life. All of these things are products of this era, of the nuclear fires that have been burning in the cores of stars for nearly 14 billion years already, and will continue for trillions more. When this era ends, the universe will still exist, but it will be a fundamentally different kind of place, a place without the energy source that has powered everything we know. It is worth pausing here to feel the weight of that. Every photon of light that has ever warmed a planetary surface came from a star. Every atom heavier than lithium that exists anywhere in the universe was forged inside a star, or in the explosion of one. Every planet that has ever formed did so in the disk of debris around a young star. The Stelliferous Era is not just one chapter of the universe's story. It is the chapter in which almost everything that makes the universe interesting, complex, and potentially alive was created. When it ends, that creative phase will be over. But ending is not the same as vanishing. The products of the Stelliferous Era will persist. The heavy elements will remain, locked into planets and stellar remnants. The structures created by 13.8 billion years, and then trillions more years of gravity and star formation will still be there. Galaxies shaped by their histories, clusters bound by dark matter, the cosmic web stretched across unimaginable distances. The universe after the Stelliferous Era will be dark and cold by comparison, but it will not be empty. It will be full of remnants, full of the ghosts of stars, full of the quiet echoes of the age that has passed. And those remnants will themselves have their own story, their own long, slow future, stretching across timescales that make even the Stelliferous Era seem brief. We are about to enter that story. We are about to step past the last star and into the next great era of the universe's history, the era not of burning suns but of cooling embers, of dense and slowly fading remnants of matter without fire. Before we go there, take a breath. Feel the warmth around you, the warmth that ultimately traces back to the nuclear fire burning in the core of the sun, a warmth that is part of the vast tapestry of the Stelliferous Era. It will last for billions of years yet, that warmth. There is no urgency here, no immediacy to what we are describing. The last star is 100 trillion years away. The sun will not exhaust itself for 5 billion years. We are in the early morning of an extraordinarily long day. But knowing that the day will eventually end, knowing what the long afternoon and evening will look like, makes the morning feel more vivid, more precious, more worthy of attention. So look up if you can in your imagination. See the stars that fill the current night sky, those hundreds of billions of suns scattered across the Milky Way, those trillions of galaxies glowing in every direction. They are not eternal. They will not always be there. But they are here now, burning as they have burned for billions of years. And that fact, the sheer improbable abundance of the present moment, is one of the most remarkable things in the entire long story of the universe. When the last red dwarf finally exhausts its hydrogen and fades, the universe will not become simply empty. It will become populated by a different kind of object entirely, objects that are in many ways the opposite of stars. Where stars are bright, these will be dark. Where stars are expanded and diffuse, these will be compressed and dense. Where stars generate energy through nuclear fusion, these will generate nothing at all, simply existing, cooling, persisting. They are the remnants of stars, the ghosts left behind after the fire goes out, and the era in which they dominate the universe is called the Degenerate Era. The name comes from the physics of how these objects are structured. Normal matter, the matter that makes up you and me, and every rock and planet and star in the universe, is held in its familiar forms by a combination of chemical and atomic forces. The atoms in a rock are held in their crystalline arrangement by the electromagnetic interactions between electrons and nuclei. The gas in a star is held in its fluid form by the thermal energy of particles bouncing off one another. But in the remnants of stars, in white dwarfs and neutron stars, the physics is different. The matter is compressed to such extreme densities that a different and more fundamental principle takes over. This principle is called the Pauli exclusion principle, and it is one of the deepest rules of quantum mechanics. It states that no two identical fermions, and electrons and neutrons are both fermions, can occupy the same quantum state at the same time. When matter is compressed tightly enough, all the low-energy quantum states become filled, and the electrons or neutrons are forced into higher and higher energy states simply because there is nowhere else for them to go. This creates a pressure called degeneracy pressure, which resists further compression with a force that is independent of temperature. It does not matter how cold a white dwarf gets. The degeneracy pressure of its electrons will continue to support it against gravity. It does not need nuclear reactions. It does not need to be hot. It simply exists, supported by the quantum mechanical refusal of its electrons to be squeezed into the same state. This is the physics that gives the Degenerate Era its name and its character. The universe becomes populated by objects whose existence depends not on fire but on quantum mechanics, not on energy generation, but on the most fundamental rules of how particles can be arranged. The transition from the Stelliferous Era to the Degenerate Era is gradual, as we have already discussed. It does not happen on a single night, or in a single billion years. It unfolds across trillions of years, as one generation of stars after another exhausts itself and leaves behind its remnant. But by the time the last red dwarfs have gone dark, the universe will be dominated by these remnants. White dwarfs, neutron stars, and black holes will be the primary objects in every galaxy, vastly outnumbering any remaining burning stars, and constituting the bulk of the ordinary matter in the cosmos. What does the Degenerate Era feel like, if one can imagine inhabiting it? The first thing that would strike any observer is the darkness. Not the cozy darkness of a bedroom at night, where the eyes gradually adjust and faint shapes become visible. A deeper, more fundamental darkness, the darkness of a universe where the primary energy sources have been extinguished, and only the residual warmth of ancient remnants remains. The white dwarfs will glow faintly, like embers in a fireplace hours after the last log has burned. Their light will be real but dim, and the distances between them will be enormous. The neutron stars will emit little or no visible light. The black holes will be invisible by definition. The universe will be, by any human standard, profoundly dark, and it will be cold. Not the cold of a winter night on Earth, which is warm by cosmic standards. The background temperature of the universe, the temperature of the cosmic microwave background radiation that permeates all of space, will continue to fall as the universe expands. Today it is about 2.7 degrees above absolute zero. By the time the Degenerate Era is well underway, it will have fallen to a fraction of a degree above absolute zero, so cold that the concept of cold itself begins to lose its ordinary meaning. The universe will be approaching the temperature floor below which thermodynamics does not allow it to go, though it will never quite reach absolute zero. The galaxies themselves will still exist in a structural sense. Gravity is patient and does not care about timescales. The Milky Way and Andromeda will have long since merged into a single large elliptical galaxy by the time the Degenerate Era arrives, a process expected to begin in about 4 billion years and complete over the following few billion. Other galaxies in the local group will have been absorbed as well, creating a large but increasingly dark and quiet structure. The dark matter halos that give galaxies their shape will still be there, invisible as always, providing the gravitational scaffolding that keeps the remnants loosely organized. But the glowing spiral arms, the blue star-forming regions, the luminous cores of active galaxies, all of that will be long gone. Within these darkened galactic structures, the white dwarfs and neutron stars will drift through space like scattered embers, moving on the long, slow orbits determined by the gravity of their galactic home. Occasionally, two remnants will pass close enough to interact gravitationally, deflecting each other's paths in a slow gravitational dance. Over vast timescales, these interactions will gradually shuffle the remnants, some gaining energy and drifting toward the outer halo of the galaxy, others losing energy and spiraling slowly inward toward the galactic center. The galaxy will be rearranging itself, slowly and silently, over timescales measured in hundreds of trillions of years. There is something strangely meditative about this picture. The Degenerate Era is not an era of events in any sense that we would currently recognize as exciting. There are no supernovae, no star births, no brilliant jets from active galactic nuclei, no warm sunlit planets with oceans and weather. There is only the slow drift of cold remnants through dark space, the gradual cooling of white dwarfs from white to yellow to orange to the deepest red, and eventually to a darkness indistinguishable from the surrounding void. There is the silent spinning of neutron stars, their rotation slowing by imperceptible degrees as they radiate their remaining energy into space. There is the patient waiting of black holes, and yet the Degenerate Era is not empty of events. There are processes happening, slow and rare by the standards of our current universe, but real and significant nonetheless. Occasionally, two white dwarfs orbiting each other will lose enough energy through gravitational wave emission to spiral together and merge, releasing a burst of energy in a type Ia supernova. These events will be extraordinarily rare by the time the Degenerate Era is well established, but they will happen. Occasionally, a white dwarf passing close enough to another object will accrete material from it, building up mass until it reaches the limit at which electron degeneracy pressure can no longer support it, whereupon it will explode or collapse. And there is one process in particular that will slowly change the Degenerate Era in a fundamental way, a process so slow that it operates on timescales that make even the Degenerate Era itself seem brief. That process is proton decay. If certain theories of particle physics are correct, and the evidence is still not conclusive, protons are not eternal. They decay, with an extremely long half-life, into lighter particles and radiation. If proton decay occurs, it will slowly dissolve the matter that makes up white dwarfs and neutron stars, turning their substance into positrons and pions and ultimately into radiation. The degenerate era will be eaten from the inside, the very building blocks of matter gradually dissolving, over timescales so enormous that the current age of the universe is to them as a single second is to the age of the universe. We will return to proton decay later in our journey. For now, let us simply settle into the degenerate era, this long, dark, cold, quiet age of remnants. It is a different universe from the one we know, but it is still a universe with structure, with physics, with objects that persist. It is the universe after the fire has gone out but before the last ember has cooled. And in that in-between state, in that long, slow twilight between the age of stars and the age of nothing, there is a strange and quiet beauty of its own. Of all the objects that will populate the degenerate era, the most common will be white dwarfs. They will be everywhere, scattered through every galaxy in numbers that will eventually exceed the current population of all stars by a significant margin, because nearly every star that has ever burned will eventually become one. The sun will become one. Most of the stars you can see on a clear night will eventually become one. White dwarfs are the standard ending of stellar life for the vast majority of stars in the universe, and in the long future, they will be the dominant form of organized matter. To understand what a white dwarf is, it helps to follow the sun's story to its conclusion. In about 5 billion years, the sun will exhaust the hydrogen in its core. Without the energy of fusion to support it, the core will contract under gravity, heating up as it does so. This heating will cause the hydrogen in the shell surrounding the core to begin fusing, releasing energy that will push the outer layers of the sun outward enormously. The sun will become a red giant, swelling to perhaps 100 to 200 times its current radius, possibly engulfing Mercury and Venus, and perhaps the orbit of Earth itself. As a red giant, the sun will burn through helium in its core, fusing it into carbon and oxygen in a phase that lasts a few 100 million years. When the helium is exhausted, the core will contract again. This time, however, the sun does not have enough mass to ignite carbon fusion. The carbon-oxygen core will simply sit there, compressed and hot, while the outer layers of the star are gradually expelled. Over about 100,000 years, the outer layers will drift away into space, forming a planetary nebula, a beautiful glowing shell of ionized gas that will slowly expand and dissipate over tens of thousands of years. What remains at the center will be the white dwarf. It will be a small, extremely dense sphere of carbon and oxygen, roughly the size of the Earth, but containing about half the mass of the Sun. A teaspoon of white dwarf material brought to Earth would weigh about 15 tons. Its surface temperature when freshly formed will be extremely high, perhaps 100,000 degrees or more, which is why it glows white. But it has no internal energy source. It is simply a hot lump of matter, and it will cool down, radiating its heat into space over billions and billions of years. The cooling of a white dwarf is a slow process of extraordinary patience. A white dwarf formed today from a star that exhausted itself early in the universe's history would still be quite warm right now, billions of years later. The oldest white dwarfs observable in the Milky Way have surface temperatures of a few thousand Kelvin, meaning they have cooled from their initial 100,000 degrees to a temperature roughly comparable to a dull, red-hot piece of metal. And they have been cooling for billions of years to get there. Project this forward. As the degenerate era unfolds over hundreds of trillions of years, the white dwarfs will continue to cool. Their surface temperature will drop from thousands of Kelvin to hundreds of Kelvin to tens of Kelvin, approaching closer and closer to the background temperature of the universe. As they cool, they will shift color. From brilliant white, they will fade to yellow, then to orange, then to dim red, then to infrared, then to wavelengths that no human eye could ever detect. At some point, they will no longer emit significant radiation at any wavelength, and they will become what are sometimes called black dwarfs. A black dwarf would be one of the most extraordinary objects in the universe. It would be a dense sphere of carbon and oxygen, crystallized by billions of years of cooling into a structure that resembles a giant diamond in some ways, supported by electron degeneracy pressure, persisting indefinitely without any energy source, simply sitting in space, cold, dark, and essentially unchanged by the passage of time. It would not decay. It would not collapse. It would not emit any detectable radiation. It would simply exist, patient and silent, a remnant of a star that once burned with the light of a sun. There is one important caveat, however. A true black dwarf, fully cooled to the background temperature of the universe, does not yet exist anywhere. The universe is not old enough. Even the oldest white dwarfs formed in the very first generations of stars are still warm by the standard of what a fully cooled black dwarf would require. Theoretical calculations suggest that white dwarfs take on the order of 10 to the 15th power years, roughly a quadrillion years, to cool to temperatures approaching the cosmic background. That is 100,000 times the current age of the universe. So while black dwarfs are a theoretical certainty, assuming proton decay does not dissolve white dwarfs first, they lie so far in the future that they have never yet existed. The idea of a black dwarf raises a question that is both simple and strange. What does it mean for something to be cold and dark and essentially static for quadrillions of years? In our ordinary experience, time brings change. Things wear down, whether rust, erode, evolve. But a black dwarf exists in a regime where almost none of those processes operate. There is no weather. There is no chemistry in the usual sense, because chemistry requires energy gradients, reactions, interactions. There is no light, no heat, no radiation. There is only the frozen crystalline structure of the carbon-oxygen interior, held in place by electron degeneracy pressure, persisting simply because quantum mechanics will not allow it to do otherwise. One might wonder whether the carbon inside a white dwarf, as it cools toward the lowest possible temperatures, truly crystallizes into something resembling diamond. The answer is yes, to a remarkable degree. The interior of a cooling white dwarf is predicted by physics to undergo a process called crystallization, in which the carbon and oxygen nuclei arrange themselves into a regular lattice structure, releasing a small amount of energy as they do so, and actually slowing the cooling process slightly. In 2019, astronomers observing a population of white dwarfs with the Gaia Space Telescope found what appears to be direct evidence of this crystallization process. A cluster of white dwarfs whose cooling had paused for longer than expected, consistent with the predicted energy release from crystallization. So the white dwarfs of the distant future will be, in some sense, giant diamonds drifting through dark space. Not composed of pure carbon in the way that gemstone diamonds are, but crystalline, ordered, dense, and extraordinarily stable. These will be among the most enduring objects in the Degenerate Era, lasting far longer than neutron stars in some models, and certainly far longer than the burning stars from which they came. Each one will be a frozen record of the star it once was, its composition, its mass, its chemical history, all encoded in the crystalline structure of its interior. But even white dwarfs, those patient and stable remnants, may not last forever. If proton decay is real, and the physics suggests it might be, Then the protons and neutrons that make up the carbon and oxygen nuclei inside a white dwarf will eventually decay, transforming the white dwarf substance into positrons and neutrinos and other lighter particles over timescales that are almost beyond description. We will discuss proton decay in detail later, but for now it is worth knowing that even these most patient of remnants have an expiration date, written in the language of particle physics, that lies so far in the future that the mind simply has to accept the number without being able to feel it. For now, as we move through the degenerate era in our imagination, let us picture the white dwarfs as they will be in their prime, warm enough to glow faintly, cooling slowly, drifting through the dark galactic structures that gravity still maintains. Each one is a sun that once was. Each one carries in its crystalline heart the history of a nuclear fire that burned for billions or trillions of years before finally going out. They are the most common remnants, the most peaceful, the most enduring in the ordinary sense. And in the long quiet of the degenerate era, they will be the closest thing to stars that the universe will have for a very long time. Alongside the white dwarfs in the degenerate era, there is another class of remnant, rarer, and in many ways even more extreme. These are the neutron stars, the collapsed cores left behind by the most massive stars, objects so dense and so strange that they represent one of the most exotic states of matter that physics currently allows. Where white dwarfs are supported by the quantum mechanical resistance of electrons, neutron stars are supported by the quantum mechanical resistance of neutrons, and the resulting objects are far smaller, far denser, and far more bizarre than anything in our ordinary experience. To understand how a neutron star forms, we need to go back to the end of a massive star's life. Stars with initial masses above roughly 8 times the mass of the Sun end their lives not gently, as white dwarfs forming from expanding planetary nebula, but violently in the catastrophic collapse of a core-collapse supernova. As we discussed earlier, when the iron core of a massive star reaches a critical mass and can no longer support itself against gravity, it collapses in less than a second, dropping from roughly the size of the Earth to roughly the size of a city, from a diameter of thousands of kilometers to a diameter of perhaps 20 kilometers, in a time span shorter than the blink of an eye. During this collapse, the density of the core reaches an extraordinary value, comparable to the density of an atomic nucleus. At these densities, the electrons and protons in the matter are forced together, combining through a process called inverse beta decay to form neutrons and neutrinos. The neutrinos stream outward in an enormous burst, carrying away most of the energy of the collapse. What remains is a sphere composed almost entirely of neutrons, packed together at nuclear density, supported against further collapse by neutron degeneracy pressure, and by the strong nuclear force that becomes repulsive at very short distances. This object, the neutron star, is one of the most extreme things in the universe. It has a mass typically between 1.5 and 2 times the mass of the Sun, but compressed into a sphere roughly 20 kilometers in diameter. Its average density is approximately equivalent to taking all of humanity, all 8 billion people on Earth, and compressing them into a volume smaller than a sugar cube. A teaspoon of neutron star material brought to Earth would weigh roughly 4 billion tons, more than the total mass of all the buildings ever constructed by humanity. The surface gravity of a neutron star is about 200 billion times the surface gravity of the Earth. If you could somehow stand on its surface, The gravitational force would be so overwhelming that even an object as small as a pea falling from 1 meter above the surface would impact with the energy of a small nuclear weapon. The surface itself is thought to consist of a rigid crystalline layer of iron nuclei arranged in a lattice, below which the density increases to the point where pure neutrons exist in a superfluid state, and below that, deeper still, the physics becomes uncertain, with some models suggesting the existence of exotic states of matter with no counterpart in ordinary experience. Neutron stars are also born spinning. The massive stars that form them rotate, and when the core collapses, conservation of angular momentum causes the rotation to speed up enormously, in the same way that a figure skater spins faster when they pull in their arms. A core that was rotating once per day might become a neutron star rotating several hundred times per second. And neutron stars have extremely strong magnetic fields, concentrated by the collapse from the already strong fields of the original star into something far more intense. These rapid rotation and strong magnetic field combine to make many neutron stars into pulsars. A pulsar is a neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the neutron star spins, these beams sweep through space like the beams of a lighthouse, and if one of them happens to sweep across the Earth with each rotation, astronomers detect a regular pulse of radio waves or X-rays arriving with extraordinary clock-like precision. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially nicknamed the signal LGM1 for Little Green Men, because the regularity of the pulses seemed almost too perfect to be natural. It was the first of thousands of pulsars now known, each one a spinning neutron star sending its lighthouse beam sweeping through the darkness. In the Degenerate Era, pulsars will gradually go silent, not because the neutron stars themselves will stop spinning, but because they will spin more slowly over time. And as they do, the processes that generate their beams will weaken. A neutron star loses rotational energy by emitting radiation, and this energy loss causes its spin to slow down by tiny but measurable amounts with each passing year. Over millions of years, a pulsar's pulse rate decreases. Over billions of years, it slows to the point where the beams can no longer be generated efficiently. And over the trillions of years of the Degenerate Era, neutron stars will spin down to such slow rates that they will become effectively silent, contributing no detectable radiation to the universe. At that point, a neutron star becomes what is sometimes called a dead neutron star, or simply a cold neutron star. It still exists. It still has its extraordinary density and mass. It still is supported by neutron degeneracy pressure, but it emits nothing significant. It is dark, dense, and cold, drifting through space on whatever orbit it has, occasionally being deflected by gravitational interactions with other remnants, but otherwise unchanged over timescales that are difficult to measure in any ordinary way. Like white dwarfs, neutron stars may eventually be affected by proton decay if that process occurs. The protons and neutrons inside them, which are themselves made of quarks held together by the strong nuclear force, may over vast timescales decay into lighter particles, slowly eroding the substance of the neutron star. But this process, if it occurs, takes place on timescales measured in numbers with 30 or more digits, so far in the future that the neutron star will have drifted through the dark universe for almost incomprehensible lengths of time before proton decay becomes relevant. There is a particular poignancy to the image of a dead neutron star drifting through the Degenerate Era. It was born in one of the most violent events in the universe, a core collapse supernova that briefly outshone an entire galaxy. It spent millions of years as a pulsar, sweeping the cosmos with its precise lighthouse beams, advertising its presence to anyone with instruments sensitive enough to hear it. And then it gradually quieted, its spin slowing, its beams weakening, until it became simply a dark, dense sphere, 20 kilometers across, moving silently through a universe that has itself grown dark and cold. Each neutron star in the Degenerate Era is a monument to the star that made it, an enduring record of the violent death of a massive sun. Occasionally, in the Degenerate Era, two neutron stars orbiting each other as a binary pair will spiral together and merge. When this happens, the result is explosive. The merger of two neutron stars releases an enormous amount of energy, producing a kilonova, an event that is far less powerful than a supernova but still briefly brilliant by the standards of a darkened universe. These mergers are also responsible for producing many of the heaviest elements in the periodic table, gold and platinum and uranium and others, which are forged in the extreme conditions of the collision and sprayed into the surrounding space. In the current universe, we see the signatures of these events. In the Degenerate Era, they will be extraordinarily rare, perhaps the brightest events in an otherwise silent cosmos, but they will still occur, brief flashes of light and chemistry in the long dark age. And sometimes the merger of two neutron stars will produce not another neutron star, but a black hole, if the combined mass exceeds the limit that neutron degeneracy pressure can support. In that case, the collision will produce a brief burst of radiation, followed by the quiet formation of another black hole, another object that will persist through the Degenerate Era and far beyond it, into the next great chapter of the universe's story. Black holes, patient and dark and enduring, will be the subjects of that chapter. But before we get there, we must pass through one more strange aspect of the Degenerate Era, the question of what happens to matter itself over the longest timescales. We have been talking about the Degenerate Era as though the white dwarfs and neutron stars within it will last more or less indefinitely, cooling slowly, drifting quietly, persisting for as long as the laws of physics allow. And if matter were truly eternal, they might. But there is a possibility, a genuine scientific hypothesis supported by several of the most promising theories in particle physics, that matter itself is not eternal, that the protons and neutrons inside every atom, inside every planet and person and star and remnant, have a finite lifespan, that they will, given enough time, decay. If proton decay is real, then the Degenerate Era will not last forever. It will come to an end through the gradual dissolution of the matter that populates it, not through any dramatic collision or explosion, but through the quiet, inevitable decomposition of the very building blocks of atoms, one proton at a time, over timescales so enormous that the entire current age of the universe, all 13.8 billion years of it, would not register as a measurable interval. To understand proton decay, it helps first to understand why protons might decay at all. In the standard model of particle physics, protons are stable. They do not decay spontaneously, and the symmetry of the standard model seems to forbid it. But the standard model is not the final word in physics. It is our best current description of the subatomic world, but it is known to be incomplete. It does not include gravity. It does not explain dark matter or dark energy. It does not account for the observed excess of matter over antimatter in the universe. Physicists have been working for decades to develop theories that go beyond the standard model, that unify its various forces and fill in its gaps. Many of these theories, collectively called grand unified theories or GUTs, predict that the proton is not truly stable. They predict that the forces that govern the behavior of quarks, the particles inside protons and neutrons, can occasionally cause a proton to transform into lighter particles. The most common predicted decay mode would see a proton transform into a positron, which is the antimatter counterpart of an electron, and a neutral pion, which is an unstable particle that almost immediately decays into 2 gamma-ray photons. The net result is that a proton, a piece of ordinary matter, converts into radiation and a particle of antimatter, which will quickly find an electron to annihilate with, producing more radiation. The key parameter is the proton's half-life, the time it takes for half of a collection of protons to decay. Experiments conducted in large underground detectors, tanks of ultra-pure water surrounded by sensitive photomultiplier tubes, have searched for the signatures of proton decay for decades without finding a definitive signal. This absence has placed a lower limit on the proton's half-life. It must be at least 10 to the 34th power years, meaning the proton lives for at least 10,000 trillion years before it is likely to decay. That number is already staggering. It is roughly a trillion times the current age of the universe. But if the proton does decay on that timescale, then the consequences for the long future are significant. White dwarfs, composed of carbon and oxygen, would slowly dissolve. Their protons and neutrons would undergo decay one by one, converting mass into radiation, the radiation streaming away into space, the white dwarf slowly losing substance over the proton decay timescale. Neutron stars would undergo the same process. The dense nuclear matter inside them would slowly be converted into positrons and pions and gamma rays, the neutron star shrinking in mass and eventually dissolving entirely. Planets would dissolve too. The Earth, the rocky worlds orbiting distant red dwarfs, the icy bodies in the far outer reaches of stellar systems, all of them composed of atoms, all of those atoms containing protons that will eventually decay. Over the proton decay timescale, all ordinary matter everywhere in the universe would be converted into radiation and leptons. The Degenerate Era would not end with a bang or a whimper. It would end through the quiet, incessant drip of proton decay, one proton decaying here, another decaying there, each decay releasing a tiny pulse of radiation that drifts away into the expanding universe. The timescale for this to complete is roughly 10 to the 40th power years, 10,000 trillion years, a number so large that writing it out in full would require 40 digits. The current age of the universe, written in years, requires 10 digits. So we are talking about a timescale 30 digits longer than the current age of the universe. If the universe's current age were a single second on a cosmic clock, the proton decay timescale would be a trillion years on that same clock. And yet, if proton decay occurs, it will happen. Every proton in every white dwarf, every neutron in every neutron star, every atom in every cold dead planet will eventually undergo this process, given enough time. The Degenerate Era will be populated by objects that are slowly dissolving at an almost incomprehensibly slow rate, their substance converting to radiation, that radiation streaming away into a universe that grows emptier and more dilute with each passing eon. There is something philosophically fascinating about this possibility. We tend to think of matter as the fundamental, persistent stuff of the universe, and of energy as something that matter produces and then loses. But proton decay, if it occurs, reverses this intuition. It says that matter is not the fundamental persistent thing. It says that matter is a temporary arrangement, a long-lived but ultimately transient form that energy takes before returning to a simpler and more diffuse state. The universe does not end with matter still present in organized forms. It ends with matter having dissolved back into the energy from which, in a very real sense, it originally came. Whether proton decay actually occurs remains one of the major open questions in physics. Current experiments have not detected it, and it is possible that the proton is genuinely stable, and that the processes we have been discussing will not occur. If proton decay does not happen, the white dwarfs and neutron stars of the Degenerate Era will persist for far longer than the timescales we have described, cooling without dissolving, drifting without decaying, present in the universe for durations that even the language of cosmology struggles to encompass. But there is another process that will eventually affect them even without proton decay, a process more certain and more exotic: quantum tunneling. Over timescales that are almost unimaginable even compared to proton decay timescales, quantum mechanics predicts that even classically stable objects will undergo spontaneous rearrangements. White dwarfs composed of carbon might, over timescales of 10 to the power of 10 to the power of 76 years, quantum tunnel into configurations of iron, the most stable nuclear configuration. This process is so slow that it makes proton decay look rapid, but it illustrates something important. Nothing in the quantum universe is truly static. Everything, given enough time, will change. For tonight's journey, we do not need to follow all of these processes to their ultimate conclusions. What matters is the overall picture. The Degenerate Era is a long, dark, cold age in which matter persists in organized forms but without the energy to be active. Whether through proton decay or through slower quantum processes, the matter of that era will eventually change, dissolve, or transform. Nothing in the universe is truly permanent. Everything is temporary, just on different timescales. And after the matter of the Degenerate Era has been exhausted, after the white dwarfs have dissolved and the neutron stars have decayed, what remains? What persists when even the most stable remnants of the stellar age are gone? The answer is the objects that do not decay through proton decay, the objects that are not made of ordinary matter at all in the usual sense, the objects that are, in a certain profound way, made of pure gravity, black holes. And the era in which they dominate the universe is the most remarkable chapter of the long future yet to come. There is a point in the long future of the universe when the last white dwarf has dissolved, when the last neutron star has decayed, when the last cold planet has had its matter quietly converted into radiation by the slow drip of proton decay, and when the universe contains almost nothing left of what we would currently recognize as ordinary matter. Almost nothing. Because there is one class of object that survives all of this, that persists through the entirety of the Degenerate Era, that emerges on the other side of proton decay intact and unchanged, waiting in the dark with the patience of something that has no internal processes to exhaust and no fuel to run out of. These are the black holes, and the era in which they are the last significant objects remaining in the universe is called, simply and appropriately, the black hole era. The black hole era is perhaps the most alien chapter of the universe's long future, because black holes are the most alien objects that physics currently describes. They are not made of matter in the way that stars and planets and white dwarfs are made of matter. They are, in the deepest sense, made of spacetime itself, of the curvature of the fabric of the universe caused by an extreme concentration of mass and energy. The matter that originally fell into a black hole is gone, converted by the collapse into a singularity, a point of infinite density that lies hidden behind the event horizon, the boundary beyond which nothing, not even light, can escape. What remains on the outside, what we interact with when we say a black hole exists, is simply a region of spacetime so curved that it traps everything. Because black holes are not made of protons and neutrons, proton decay does not affect them. They will sail through the degenerate era unchanged, while everything else around them slowly dissolves. They will watch, if watching were something black holes could do, as the white dwarfs and neutron stars and cold, dark planets all gradually lose their substance to proton decay, converting their mass into radiation that drifts away into the expanding universe. And when all of that is done, when the matter of the degenerate era is exhausted, the black holes will still be there. How many black holes will there be at this point? The answer depends on processes that are difficult to calculate precisely, but the broad picture is clear enough. Every star with an initial mass above roughly 20 to 30 times the mass of the Sun ends its life as a black hole. In the current universe, there are estimated to be somewhere between 100 million and 1 billion stellar mass black holes in the Milky Way alone. Each galaxy in the observable universe has a similar population. On top of these stellar mass black holes, there are the supermassive black holes at the centers of most galaxies, objects containing millions to billions of times the mass of the Sun, formed through a combination of direct collapse and billions of years of accretion and merging. By the time the black hole era begins, in the far distant future after the degenerate era has run its course, the black holes will have accumulated additional mass through the occasional capture of passing matter and the occasional merger with one another. The supermassive black holes at the centers of galaxies, or rather of the merged galactic remnants that will exist by then, may have grown to truly enormous sizes, containing masses equivalent to billions or even tens of billions of suns. The stellar mass black holes will have drifted further apart as the galactic structures they inhabit gradually dissolve, but they will still be there, patient and dark and invisible, scattered through the vast spaces that were once filled with light. The universe at the beginning of the black hole era will be a place of extraordinary emptiness by any standard we might apply. The background temperature will be so close to absolute zero that the difference is essentially meaningless in practical terms. The expansion of the universe will have stretched the distances between objects to scales that make current cosmological distances seem intimate. Individual black holes will be separated by distances so enormous that even the concept of a galaxy will have lost its meaning. There will no longer be galaxies in any structural sense, because the galaxies will have gradually dissolved over the course of the degenerate era, their constituent objects drifting slowly outward as gravitational interactions over enormous timescales gradually unbind them. This dissolution of galaxies deserves a moment of attention, because it is a process that happens on a timescale that is long even by the standards of the degenerate era. Galaxies are bound by gravity, and gravity is patient. The individual stars and remnants in a galaxy are not going to simply fly apart on their own. But over timescales of roughly 10 to the 19th power years, which is 10 billion years, the cumulative effect of countless small gravitational interactions between objects in the galaxy will cause the galaxy to evaporate. Most of its members will gradually gain enough energy from these interactions to escape the galaxy's gravitational well and drift away into intergalactic space. A small fraction will lose energy and spiral inward, eventually being consumed by the central black hole. This is not a dramatic process. There is no explosion, no sudden dispersal. It is simply the slow statistical consequence of the fact that in any gravitational system, random interactions will over time transfer energy from some members to others, with the lucky ones gaining enough energy to escape and the unlucky ones sinking inward. Given enough time, a galaxy will evaporate the way a glass of water evaporates, not all at once, but molecule by molecule, or in this case, object by object over timescales that make the current age of the universe negligible by comparison. By the time this process is complete, the black holes will be essentially isolated in the expanding universe, each one drifting alone in an enormous volume of nearly empty space. The supermassive black holes will have consumed whatever fell their way during the evaporation of the galaxies, growing slightly larger. The stellar mass black holes will be scattered in the surrounding darkness, most of them too small and too distant from anything to accrete significant mass. All of them will be invisible, contributing no light to the universe, their presence detectable only by the gravitational distortion of their surroundings. Imagine the universe at this point, not as a place of darkness that feels like the absence of something, but as a vast and almost incomprehensibly empty space in which isolated black holes drift, separated by distances that no journey could bridge in any practical sense. In a cosmos whose background temperature is a tiny fraction above absolute zero, whose expansion continues carrying everything farther and farther from everything else. No light, no warmth, no chemistry, no structure in the familiar sense of the word. Just the black holes, patient and ancient, carrying within their event horizons the compressed memory of the stars and galaxies and civilizations that once filled the universe with such extraordinary richness. And yet, even in this extreme emptiness, something is happening. Something is happening very slowly, almost imperceptibly slowly, but happening nonetheless. The black holes are not truly static. They are not truly eternal. They are leaking, radiating away their mass in the most subtle and most quantum of ways, through a process that was first predicted by the physicist Stephen Hawking in 1974, a process that bears his name, and a process that will, given enough time, cause every black hole in the universe to evaporate completely. Hawking radiation is the mechanism by which the black hole era will eventually come to an end. It is the process that will dissolve the last objects in the universe and bring the cosmos one step closer to its final, darkest, most silent state. To understand it, we need to spend some time with one of the strangest and most profound ideas in all of physics. We need to spend some time with the quantum nature of empty space. Before we can understand how black holes will slowly dissolve and carry the universe into its next era, it helps to spend some time with what black holes actually are. Not just the dramatic shorthand of objects so dense that light cannot escape, though that is true, but the deeper picture of what physics tells us about the nature of these extraordinary objects, about the geometry of space-time around them, about the event horizon and what it means, and about why the laws of physics themselves seem to reach their limits when confronted with what lies inside one. Black holes were predicted by Einstein's general theory of relativity, which he published in 1915. General relativity describes gravity not as a force in the Newtonian sense, not as an invisible pull between masses transmitted across empty space, but as a curvature of spacetime itself. Massive objects warp the fabric of spacetime around them, and other objects moving through that warped spacetime follow curved paths, which we experience as the effect of gravity. The Earth curves spacetime around it, and the Moon follows a curved path through that warped region, which is what we call its orbit. The Sun curves spacetime more deeply, and the planets follow their orbits in response. The more massive an object, the more deeply it curves the spacetime around it. General relativity's equations, when applied to the simplest possible case of a perfectly spherical mass, produce a solution discovered by the physicist Karl Schwarzschild in 1916, just months after Einstein published his theory. The Schwarzschild solution describes the spacetime geometry around a spherically symmetric mass, and it reveals something remarkable. For any given mass, there is a radius called the Schwarzschild radius at which the curvature of spacetime becomes so extreme that the escape velocity, the speed you would need to escape the gravitational pull, equals the speed of light. Inside this radius, not even light has enough speed to escape. This radius defines the event horizon of a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. This means that if you could somehow compress the entire mass of the Sun into a sphere 3 kilometers in radius, the resulting object would be a black hole. The Sun's actual radius is about 700,000 kilometers, so it is nowhere near being a black hole. But if a massive star, with 10 or 20 or 50 times the mass of the Sun, exhausts its nuclear fuel, and its core collapses below the relevant Schwarzschild radius, a black hole will form. The event horizon is not a physical surface. There is no wall there, no membrane you could touch if you somehow survived the journey to it. It is simply a boundary in spacetime, a point of no return. An astronaut falling into a black hole would cross the event horizon without noticing anything particularly dramatic at that moment, because locally, in their immediate surroundings, spacetime looks perfectly normal. But they would have passed a threshold from which there is no return. Everything from that point on, every possible path that physics allows, leads inward, toward the singularity at the center. There is no path back out, not because the forces are too strong to overcome, but because in the warped geometry of spacetime inside the event horizon, there is no direction that points outward. All directions lead inward. The future, for anything inside the event horizon, includes only the singularity. The singularity at the center of a black hole is the point at which the equations of general relativity break down completely. The theory predicts infinite density, infinite spacetime curvature, a point at which the mathematical description ceases to be meaningful. Physicists generally believe that a singularity in a theory's equations indicates that the theory is incomplete, that it is being pushed beyond its domain of validity. At the singularity, we would need a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics to describe what is actually happening. We do not yet have such a theory, and so the interior of a black hole remains, in a very real sense, one of the deepest mysteries in all of physics. What we do know is that the mass of everything that has ever fallen into a black hole is encoded in the black hole's properties. A black hole is described entirely by just 3 numbers: its mass, its electric charge, and its angular momentum, which measures how fast it is spinning. This is known as the no-hair theorem, expressed colloquially as the idea that black holes have no hair, meaning no additional structure or detail beyond these 3 quantities. Two black holes with the same mass, charge, and spin are completely identical. All the history, all the structure, all the information about what fell into them is gone from any outside perspective, compressed into those three numbers. This leads to one of the deepest puzzles in modern physics, known as the black hole information paradox. In quantum mechanics, information is never truly destroyed. The quantum state of a system at one time determines its state at all future times, at least in principle. But if everything that falls into a black hole is reduced to just three numbers, what happened to all the information about the infalling matter? Was it destroyed, violating quantum mechanical principles? Or is it somehow preserved, encoded in the black hole in a way we do not yet understand? Stephen Hawking originally argued that information is destroyed in black holes, which caused a profound controversy in physics that has lasted decades. Most physicists today believe that information is somehow preserved, but the exact mechanism by which this happens remains an active area of research and debate. Black holes come in a range of sizes. Stellar mass black holes, formed from the collapse of massive stars, have masses ranging from roughly 3 to perhaps 100 times the mass of the Sun. Intermediate mass black holes, with masses between a few hundred and a few 100,000 solar masses, are thought to exist but are harder to detect and less well understood. And supermassive black holes, found at the centers of most large galaxies, range from about 1 million to tens of billions of solar masses. The supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4 million solar masses and would fit comfortably inside the orbit of Mercury. The most massive black holes known are the ultramassive black holes found at the centers of the largest elliptical galaxies, some of which may contain masses of tens of billions of solar masses. These objects, when they are actively feeding on surrounding gas and dust, produce the phenomena we call quasars, or active galactic nuclei, some of the most luminous objects in the observable universe, outshining their entire host galaxies by factors of hundreds. In the current universe, many supermassive black holes are relatively quiescent, no longer fed by the large amounts of gas that fueled their growth in the early universe. They sit at the centers of their galaxies, massive and dark, contributing their gravity but emitting no significant radiation. In the black hole era, these supermassive black holes will be the largest and most massive objects remaining in the universe. They will have consumed whatever matter remained in their vicinity as the Degenerate Era concluded. They will be ancient beyond any description that our current experience provides. They will be, in a very real sense, the last large-scale structures in the universe, the final inheritors of the mass and energy that once filled the cosmos with light. And they will be evaporating. Slowly, almost impossibly slowly, but evaporating nonetheless. The mechanism by which they do so is Hawking radiation, and understanding it requires us to take one more step into the strange world of quantum mechanics, into the nature of the vacuum, into the reality that empty space is not as empty as it appears. In 1974, the physicist Stephen Hawking published a paper that shocked the scientific community and changed our understanding of black holes forever. The paper showed, through a calculation that combined general relativity and quantum mechanics in a way no one had previously attempted, that black holes are not truly black. They emit radiation, slowly, continuously, and at a temperature that depends on their mass. Every black hole in the universe is radiating energy into the surrounding space, losing mass with each passing moment, and will eventually, given enough time, evaporate completely. This result was so surprising, so counterintuitive, that many physicists initially doubted it. Black holes were supposed to be the ultimate one-way doors. Things go in and nothing comes out. That was the whole point. And yet here was Hawking's calculation, derived from sound physics, showing that something does come out. Not from inside the event horizon, not in violation of relativity, but from the region just outside it, through a process that is fundamentally quantum mechanical in nature. To understand where Hawking radiation comes from, you need to know something about the quantum nature of empty space. In classical physics, empty space is just that, empty. A vacuum contains nothing and there is nothing to say about it. But in quantum mechanics, the vacuum is a much stranger and richer place. The uncertainty principle, one of the foundational principles of quantum mechanics, states that certain pairs of physical quantities cannot both be known precisely at the same time. Position and momentum are one such pair. Energy and time are another. The energy-time uncertainty principle has a profound consequence for empty space. It means that the energy of a region of space cannot be precisely zero for precisely zero time. There must always be some quantum fluctuation, some tiny temporary deviation from perfect emptiness. These fluctuations take the form of pairs of virtual particles, particle-antiparticle pairs that spontaneously appear and almost immediately annihilate each other, their existence so brief that they cannot be directly detected, borrowing energy from the vacuum for an instant before returning it. This is not a speculative idea. The effects of these virtual particle pairs can be detected in precision experiments, and they have been, in phenomena like the Casimir effect and the Lamb shift, which show measurable consequences of the quantum vacuum's activity. Normally, when a virtual particle-antiparticle pair appears in empty space, both particles annihilate before either can become real. They appear, exist for a fleeting moment dictated by the uncertainty principle, and then disappear, leaving no net effect on the energy of the region. But at the event horizon of a black hole, something different can happen. If a virtual particle pair appears very close to the event horizon, one particle of the pair may fall inside the horizon while the other escapes. When this happens, the escaping particle can no longer annihilate with its partner, because its partner has fallen into the black hole. The escaping particle becomes real, carrying genuine energy away from the black hole, and the energy for this has to come from somewhere. It comes from the black hole itself, which loses a tiny amount of mass with each such event. The radiation that streams away from the black hole through this process is called Hawking radiation, and it has the mathematical properties of thermal radiation, the kind of radiation emitted by any warm object. The black hole radiates as though it has a temperature, and that temperature is inversely proportional to the black hole's mass. A more massive black hole has a lower Hawking temperature. A less massive black hole has a higher temperature and therefore radiates more intensely. This creates a feedback loop with a remarkable consequence. As a black hole loses mass through Hawking radiation, it becomes less massive, which raises its temperature, which increases its rate of radiation, which causes it to lose mass faster, which raises the temperature further, and so on, in an accelerating cascade that ends in the complete evaporation of the black hole in a final burst of radiation. For the black holes of the current universe, Hawking radiation is so incredibly faint that it is completely unmeasurable and cosmologically irrelevant. A black hole with the mass of the Sun would have a Hawking temperature of about 60 billionths of a Kelvin, far below the temperature of the cosmic microwave background, which means it would actually absorb more radiation from the background than it emits through Hawking radiation. Under current conditions, black holes are gaining mass from the background radiation faster than they are losing it through Hawking evaporation. They are, if anything, growing slightly. But as the universe expands and cools, the temperature of the cosmic microwave background will continue to fall. It is currently about 2.7 Kelvin. As the universe ages, it will drop lower and lower, toward absolute zero. At some point in the future, the background temperature will fall below the Hawking temperature of even the most massive black holes, and from that moment on, Hawking evaporation will begin to dominate. The black holes will start to lose mass net, slowly at first, but irreversibly. How long will it take for a black hole to evaporate completely through Hawking radiation? The calculation depends on the black hole's mass, and the answer scales with the cube of the mass. Double the mass of a black hole and it takes 8 times as long to evaporate. The evaporation time for a stellar mass black hole of perhaps 10 solar masses is estimated at roughly 10 to the 74th power years. That is an incomprehensibly large number, a 1 followed by 74 zeros, many orders of magnitude longer than the proton decay timescale we discussed earlier, which was only 10 to the 40th power years. For supermassive black holes, the timescales are even more extreme. A black hole of 1 billion solar masses would take roughly 10 to the 96th power years to evaporate. The largest black holes in the universe, if any, have grown to truly enormous sizes through mergers during the black hole era, might take up to 10 to the 106th power years to evaporate completely. These numbers are so large that they require a moment of simple acknowledgement. We are not talking about a long time in the way that a million years or a billion years is a long time. We are talking about duration so far beyond any human reference point that the only honest response is to let the numbers stand without trying to feel them directly. During the vast majority of the evaporation time, the black hole changes almost imperceptibly. A supermassive black hole evaporating over 10 to the 96th power years will spend most of that time as a very slightly smaller version of what it was at the start of the black hole era. The rate of mass loss scales as the inverse square of the mass, which means that a more massive black hole loses mass proportionally more slowly. For most of the evaporation period, the black hole is emitting Hawking radiation at such a low rate that the energy output is completely negligible. The universe is dark and the black hole is leaking, but the leak is so slow that it is effectively indistinguishable from nothing. Only in the final moments of a black hole's life does the evaporation process become dramatic. In the last fractions of a second, as the black hole's mass drops to near zero and its temperature rises toward astronomical values, the radiation output increases enormously, reaching a climax in a final burst of high-energy particles and photons that briefly illuminates the surrounding darkness. This final explosion releases the equivalent of all the mass energy remaining in the black hole, converting it to radiation in a brief but intense flash. And then the black hole is gone. The event horizon has shrunk to nothing. The singularity has dissolved. What was once an object that captured everything and released nothing has finally given back all that it had in a last quiet firework in the deep dark of an almost empty universe. And after it is gone, the space it occupied is just space again. Empty, expanding, cold. There is no crater, no remnant, no scar in space-time. The black hole simply ceases to exist, and the universe contains one fewer black hole than it did before. Eventually, one by one, across timescales of unimaginable length, all the black holes will follow the same path. The stellar mass ones will go first, their smaller masses making their evaporation times shorter. Then the intermediate mass ones. Then the supermassive ones. And finally, if any truly enormous black holes have formed through mergers during the long ages of the black hole era, those last behemoths will go as well, their final moments marked by the last significant energy releases in the history of the universe. When the last black hole evaporates, the black hole era is over, and what the universe enters next is something for which the word era almost seems too lively a description. It is the dark era, the final age, the long silence that follows everything else. But that silence has its own strange story to tell, and we will follow it all the way to the end. There is a particular kind of solitude that belongs to the last of something, the last member of a species, the last speaker of a language, the last building standing in a city that has been gradually abandoned. There is something about finality that carries its own weight, its own particular quality of presence, precisely because it is about to become absence. In the long future of the universe, the last black holes carry that quality in a way that no other objects ever will, because they are not merely the last of their kind. They are the last of everything, the final significant structures in a universe that has spent unimaginable eons gradually simplifying itself down to almost nothing. Let us follow the black hole era to its conclusion, taking our time, because the story of the last black holes deserves careful attention. It is a story about patience more absolute than anything else in the history of the cosmos. The black holes that will be last to evaporate are the largest ones, the supermassive and ultramassive black holes that formed at the centers of galaxies and grew through billions of years of accretion and merging. These objects, by the time the black hole era is well established, will be ancient in a way that has no adequate comparison. They will have existed since before the Degenerate Era began. They will have watched the white dwarfs cool and dissolve, and the neutron stars decay, and the very substance of matter evaporate around them, unchanged throughout it all. During the black hole era, black holes will occasionally encounter one another and merge. As galaxies evaporated during the late Degenerate Era, their central black holes merged into increasingly large objects. Some of these mergers will continue into the black hole era proper, as isolated black holes drift through the expanding universe and occasionally pass close enough to be captured by each other's gravity, spiraling together over enormous timescales as they lose energy through gravitational wave emission. Each merger will produce a brief burst of gravitational waves, a ripple in space-time that propagates outward through the dark universe, carrying energy away from the newly merged and now slightly larger black hole. Gravitational waves are themselves a remarkable thing to contemplate in the context of the black hole era. In the current universe, gravitational wave astronomy is a young and exciting field. The LIGO and Virgo observatories have detected dozens of gravitational wave events, mostly from the mergers of stellar mass black holes and neutron stars, and each detection has opened a new window on the universe. In the black hole era, gravitational waves from black hole mergers will be essentially the only significant events happening in the universe. They will be the only perturbations in the otherwise featureless silence, brief tremors in space-time that announce the collision and union of two ancient objects, followed by the continued darkness of an only slightly larger black hole drifting alone in the void. After the mergers come the long evaporations. The largest black holes that exist at the peak of the black hole era will have masses that might range from the masses of original supermassive black holes to potentially much larger objects formed through multiple mergers. For a black hole of 1 billion solar masses, the evaporation time through Hawking radiation is on the order of 10 to the 83rd power years. For a black hole of 10 billion solar masses, it is roughly 10 to the 96th power years. For truly enormous black holes formed through many mergers, perhaps containing the mass of trillions of suns, the evaporation time could stretch toward 10 to the 106th power years or beyond. These numbers represent a duration so extraordinary that the only way to approach them is to simply sit with the fact of their enormity without trying to convert them into anything familiar. There is no analogy that does justice to the difference between 100 trillion years and 10 to the 106th power years. The ratio between those two numbers is itself a number with more than 90 digits. It is not that the black hole era is a long time. It is that the black hole era redefines what the word long means. During most of the black hole era, the universe presents an almost perfectly uniform picture of emptiness. Individual black holes are scattered through an expanding void, each one isolated, each one emitting Hawking radiation so faint that its energy output is essentially zero compared to any reference standard from the current universe. The universe is dark, not the dramatic darkness of a cave or a windowless room, but the darkness of a space where the photon density is so low and the temperature so close to absolute zero that darkness is the only accurate word. The background radiation of the universe, the cosmic microwave background that today permeates all of space and connects every part of the universe to the moment of its birth, will by this point have been stretched by the ongoing expansion to wavelengths so long and energies so low that it barely qualifies as radiation in any meaningful sense. The photons of the cosmic microwave background will be separated by distances comparable to the sizes of galactic clusters, each one an isolated quantum of energy drifting through an enormous emptiness. The universe will have become, in the most literal possible sense, a near-perfect vacuum. In this context, the black holes are the only concentrations of anything. They are the only places in the universe where a significant amount of mass energy is gathered into a defined region of space. They are the last islands in a sea that has become almost incomprehensibly dilute, and one by one, over their respective evaporation timescales, they are draining away into Hawking radiation that quickly spreads into the surrounding void. Each time a black hole loses enough mass to warm its Hawking temperature significantly, its rate of evaporation increases. For most of the evaporation period, this increase is negligible from any outside perspective. A black hole that has lost 1% of its mass in a trillion years will lose the next 1% slightly faster, but not in any way that could be perceived without instruments of extraordinary sensitivity. The process is gradual almost to the point of being static. It is only in the very final stages, as the mass drops low enough that the temperature climbs to notable values, that the evaporation becomes perceptible as a process rather than as a static condition. In the final seconds of a large black hole's life, something that could be called dramatic does occur. The temperature rises from fractions of a Kelvin to thousands to millions to billions of Kelvin in the last fractions of a second, and the radiation output climbs correspondingly. The final burst is a flash of high-energy particles and photons, an explosion that, brief as it is, represents the release of the last mass energy of an object that may have existed for longer than 10 to the 100th power years. And then the Hawking temperature formally becomes infinite as the mass approaches zero and the black hole ceases to exist. What is left after the last black hole evaporates? Photons, gravitons, neutrinos perhaps, though their exact fate over such timescales depends on physics we do not yet fully understand. A handful of electrons and positrons, or perhaps none at all. The extremely dilute remnants of the Hawking radiation, emitted by every black hole that has ever evaporated, spread across a universe that has expanded so enormously that the average density of anything is effectively zero. The Hawking radiation from the final evaporating black holes will spread outward and join the unimaginably dilute sea of radiation that is all that remains of everything the universe has ever been. There is something almost tender about this image. The black holes, which began as the most violent and dramatic objects in the universe, the endpoints of catastrophic stellar collapse, the engines of quasars that outshone entire galaxies, the final survivors of the age of matter, end their existence by giving back the energy and mass they consumed over the course of cosmic history, returning it to the universe in the form of radiation, completing the long, slow cycle from matter to energy that has been running since the first stars ignited and will not conclude until the last black hole releases its final photon. After that, there are no black holes. There are no stars. There are no remnants. There is no matter in any organized form. There is only the dark era, the last and longest and quietest age that the universe will ever know. After the last black hole has evaporated and released its final burst of Hawking radiation into the surrounding void, the universe enters an age that has no precedent in any of the eras we have discussed so far. The Stelliferous Era had stars. The Degenerate Era had remnants. The Black Hole Era had black holes. Each of these eras had something in it, some kind of organized, persistent structure that gave the era its character and its name. But the Dark Era, the age that follows the Black Hole Era, has almost nothing. It is the closest the universe will ever come to being genuinely, comprehensively empty. The Dark Era is not simply dark in the way that a night sky is dark, where darkness is the absence of the specific light that human eyes can see. It is dark in the sense that there are no significant sources of energy anywhere in the observable universe. There are no nuclear reactions happening. There are no gravitational collapses releasing heat. There are no chemical reactions producing light. There are no accretion disks glowing as matter falls toward massive objects. There are no massive objects. There is nothing concentrated enough to generate any of these processes. The universe is spread out into a thin, cold, nearly uniform sea of elementary particles and photons, expanding through space-time that continues to grow larger and emptier with every passing moment. What exactly populates the Dark Era? The answer is a very short list. There are photons, the particles of light and radiation that were produced throughout all of cosmic history and have been spreading outward ever since, their wavelength stretched by the expansion of the universe to longer and longer values, their energies diminishing toward the irreducibly small. The photons from the original cosmic microwave background, from the first light of stars, from billions of years of stellar radiation, from countless supernovae, from the Hawking radiation of every black hole that ever evaporated, all of these will be present in the Dark Era, spread across an unimaginable volume of space, so dilute that the average distance between any two photons will be enormous. There are also leptons, the lightest fundamental particles, primarily electrons and positrons that escaped annihilation through various processes over the course of cosmic history. Whether significant numbers of these particles will remain in the dark era depends on physics that we do not fully understand. If equal numbers of electrons and positrons were produced, they would eventually find each other and annihilate, contributing their energy to the photon sea. If there is a slight imbalance, as there appears to be in the current universe between matter and antimatter, some electrons may remain as isolated particles drifting through the void. There may be neutrinos. Neutrinos are the most elusive of all fundamental particles, interacting with everything else through only the weak nuclear force and gravity. They have a tiny but non-zero mass, and they are extraordinarily numerous. The universe is currently filled with a background of cosmic neutrinos left over from the Big Bang, about 336 neutrinos per cubic centimeter of space on average. In the dark era, these neutrinos will still be present, their density diluted by the expansion of the universe, but their total number conserved. Whether neutrinos will decay over the timescales of the dark era is unknown, because it depends on the details of neutrino physics that remain incompletely understood. And there are gravitons, the hypothetical quantum particles of gravitational waves, assuming that gravity is indeed quantized in the way that the other forces are. If gravitons exist, the universe will contain a background of cosmic gravitons produced throughout its history, analogous to the photon background. Like the photons, they will spread through the expanding universe, their wavelengths stretched and their energies diminished, contributing their tiny share to the diffuse energy content of the dark era cosmos. Beyond these fundamental particles, there is almost nothing. The dark era is a universe in which complexity has been completely exhausted. Every form of organized matter, from galaxies to stars to planets to atoms to protons and neutrons, has either been destroyed by proton decay or dissolved by the Hawking evaporation of black holes. What remains is the irreducible minimum, the simplest possible particles spreading through the simplest possible space. The temperature of the dark era universe is so close to absolute zero that the difference is effectively unmeasurable in any practical sense. The background temperature will continue to fall as the universe expands, dropping to values so small that writing them as ordinary fractions would require strings of zeros after the decimal point so long that the string itself would fill many pages. The universe is not quite at absolute zero, because there are still photons present with some non-zero energy. But the difference between the temperature of the dark era universe and absolute zero is so small as to be philosophically rather than practically significant. The expansion of the universe continues. Dark energy, that mysterious component of the cosmos that causes the expansion to accelerate, will presumably still be present in the dark era, still driving the universe to grow larger. As it does, the already unimaginably dilute sea of particles and photons will become still more dilute. The average distance between any two particles will continue to grow. The universe will become emptier and emptier, not by losing particles, but by becoming larger while the number of particles remains fixed. In the very far future of the dark era, even the occasional interaction between particles, the rare collision of a photon with an electron, the even rarer collision of two electrons, will become so infrequent as to be effectively non-existent. The universe will approach a state of complete isolation, each particle a universe unto itself, surrounded by an expanding void so large that it will never interact with anything else again. The word loneliness is too human a concept for this, too small for the scale, but it captures something of the character of the dark era. Each particle, if particles can be said to have a condition, will be alone in a way that has no equivalent in any experience that consciousness has ever had. Is there anything happening in the dark era? Is there any process, any event, anything at all that disturbs the silence? The answer, perhaps surprisingly, is yes, though the processes are so slow and so subtle that saying they are happening is almost as misleading as saying they are not. There are quantum fluctuations. Space, even in the dark era, is not a perfect classical vacuum. The same quantum vacuum energy that gave rise to Hawking radiation will still be present, virtual particle pairs still flickering in and out of existence for unmeasurably brief moments, contributing their tiny effects to the structure of the quantum vacuum. These fluctuations do not produce anything lasting in the dark era. They appear and disappear without consequence. But they exist, a faint echo of the quantum activity that once populated the universe with Hawking radiation and particle physics. There is also, at timescales almost beyond description, the theoretical possibility of fluctuations large enough to be significant. The physicist Ludwig Boltzmann, in the 19th century, speculated about the possibility of statistical fluctuations in a universe at thermal equilibrium, random arrangements of matter and energy that, given enough time, might spontaneously produce ordered structures purely by chance. The most famous of these speculative objects is called a Boltzmann brain, a hypothetical self-aware entity that might arise, spontaneously and briefly, as a random fluctuation of matter and energy in a universe that has reached maximum entropy. Whether Boltzmann brains or any other large-scale fluctuations are physically possible in the dark era depends on deep questions about the nature of the quantum vacuum and the ultimate fate of space itself that physics cannot currently answer. But the speculation itself is interesting because it highlights the strange relationship between time and possibility in a universe of infinite duration. If the dark era truly lasts forever, then any event that has a non-zero probability, however small, will eventually occur. And the probability of a random fluctuation producing an ordered structure, while absurdly small by ordinary standards, may not be exactly zero. This is one of the deepest and strangest aspects of thinking about the very long-term future. In a universe old enough, the ordinary rules of what is likely and what is unlikely begin to break down. The universe becomes a place where the extraordinarily improbable has, by definition, had enough time to happen. What this means in practice, whether it means anything at all, is one of the open questions at the frontier of cosmology and philosophy. But for now, let us simply sit with the dark era as a place, a condition, a state of the universe that will exist for longer than all of the eras we have discussed so far put together. The dark era is not a brief epilogue to the more interesting chapters of cosmic history. It is, in terms of raw duration, the dominant feature of the universe's timeline. If the universe is eternal, then the dark era is essentially everything. All the eras before it, including the black hole era with its unimaginable timescales, are merely a brief introduction, a preface to the long silence that follows. To understand why the universe is heading where we have been describing, why it moves from richness and complexity toward darkness and stillness, why the story we are telling has the shape it has, with a beginning full of energy and fire, and an ending full of silence and cold, you need to understand one of the most fundamental concepts in all of physics. You need to understand entropy, because entropy is not simply a technical term in thermodynamics. It is the reason the universe has a direction. It is the reason time flows one way and not the other. It is the deep physical law that underlies the entire long story we have been following tonight. From the burning stars of the Stelliferous Era, to the evaporating black holes of the black hole era, to the silent particles of the dark era. Entropy is often described as a measure of disorder, and while that description is useful, it is also somewhat misleading if taken too literally. A better way to think about entropy is as a measure of the number of possible ways a system can be arranged while still looking the same from a macroscopic perspective. A gas in which all the molecules are packed into one corner of a container has low entropy because there are relatively few arrangements of the molecules that would produce that configuration. The same gas spread evenly throughout the container has high entropy because there are vastly more arrangements of the individual molecules that would produce that uniform distribution. The gas spreading from the corner to fill the whole container is not moving toward disorder in any mystical sense. It is simply moving toward the arrangement that has the most possibilities, the most ways of being realized. The second law of thermodynamics states that the entropy of an isolated system tends to increase over time. It tends to move from less likely arrangements to more likely ones, from concentrated and structured configurations to spread out and uniform ones, from low entropy to high entropy. This is not a law that can be violated, because it is built into the statistical foundations of how large numbers of particles behave. Any particular low entropy arrangement is simply less probable than a high entropy one, and over time, systems wander from less probable states to more probable states simply by chance, and they do not wander back, because the more probable states are so overwhelmingly more numerous. Applied to the universe as a whole, the second law of thermodynamics says something profound. The universe began, at the moment of the Big Bang, in an extraordinarily low entropy state. All the matter and energy of the cosmos was concentrated in an almost perfectly uniform, extremely hot, extremely dense configuration. This might sound like a high entropy state, like maximum disorder, but it was actually a state of very low entropy from the gravitational perspective. Gravity makes uniformity a low entropy state, because gravity wants to pull matter together into concentrated clumps, into stars and galaxies and black holes, and a uniform distribution represents a very specific and unlikely configuration from the standpoint of gravitational physics. Since the Big Bang, the universe has been increasing its entropy. The initially uniform distribution of matter has clumped under gravity into stars and galaxies, releasing gravitational energy as heat and radiation. Stars have converted hydrogen into heavier elements and released energy as starlight, spreading that energy outward into the surrounding space, increasing the entropy of the cosmos. Supernovae have scattered heavy elements across galaxies, enriching the interstellar medium and increasing the diversity and complexity of the chemical environment, but also increasing entropy in the thermodynamic sense. Black holes have formed and will eventually evaporate, spreading the mass energy of collapsed stars back into radiation and contributing to the universal increase of entropy. The endpoint of this relentless increase is what physicists call the heat death of the universe. The heat death does not involve anything dramatic. It does not involve fire or explosion or any kind of energetic event. It is, in fact, the absence of all energetic events. The heat death is the state in which the universe has reached maximum entropy, the state in which matter and energy are so thoroughly spread out and so perfectly uniform that no further increase in entropy is possible, because the maximum has already been reached. In this state, there are no temperature gradients, no energy flows from one region to another, no processes of any kind, because all processes require a difference, a gradient, a flow from somewhere more concentrated to somewhere less concentrated. And in the heat death state, no such differences remain. The heat death is not a moment. It is a condition that the universe approaches gradually, asymptotically, like a curve that gets closer and closer to a line without ever quite reaching it. As each era passes, the universe moves closer to this condition. The Stelliferous Era reduces temperature gradients by spreading starlight through the cosmos. The Degenerate Era eliminates the most extreme concentrations of matter. The Black Hole Era removes the most extreme concentrations of mass energy. And the Dark Era represents the universe hovering very near the heat-death condition, close enough that the remaining deviations from perfect uniformity are negligible in any practical sense. Whether the universe actually reaches perfect maximum entropy, whether the heat death is a state the universe truly achieves or merely approaches without limit, is a question that current physics cannot definitively answer. If the universe is infinite in size, then the total entropy of the universe is already infinite in some sense, and the concept of maximum entropy becomes more complex. If the universe is finite but unbounded, the answer depends on the ultimate fate of dark energy and the geometry of space. These are open questions at the frontier of cosmology, but the direction is clear, regardless of the endpoint. The universe moves toward greater entropy. It moves from concentration to dilution, from hot to cold, from structured to uniform, from complex to simple, from the brilliant chaos of the Stelliferous Era to the near-perfect stillness of the Dark Era. Every physical process we have described tonight, the burning of stars, the cooling of white dwarfs, the decay of protons, the evaporation of black holes, all of these are steps in the same direction. All of them are the universe moving toward the most probable state, toward the arrangement that has the greatest number of ways of being realized, toward the condition that physics calls maximum entropy, and that we might simply call rest. There is something almost peaceful about understanding entropy in this context. The universe is not being destroyed. It is not being erased. It is reaching equilibrium, finding its most natural and most stable condition, the condition in which everything is as uniform and as spread out and as quiet as it can possibly be. From a certain angle, the heat death of the universe is not a tragedy. It is a completion. It is the universe finding, at the end of an unimaginably long journey, the state of rest that the second law of thermodynamics has always been pointing it toward. For us, living in the Stelliferous Era, living in one of the most extreme low entropy configurations the universe will ever host, with its blazing stars and swirling galaxies and warm planets and living things, the heat death seems impossibly remote. And it is. It will not arrive for timescales that make the Stelliferous Era itself seem negligible. But the direction of travel has been set since the moment of the Big Bang. Every star that burns, every black hole that evaporates, every particle that drifts through the expanding void is part of the same slow, inevitable, patient journey toward the silence of maximum entropy. Understanding this gives the whole story of the universe's future a kind of coherence, a narrative logic that runs from beginning to end without interruption. The universe began in a state of low entropy and extreme concentration. It has been moving toward high entropy and diffusion ever since. The eras we have been discussing are the chapters of that journey, each one a step further along the path, each one slightly quieter and slightly more uniform than the one before. And at the end of the path, if an end exists, is the heat death, the final equilibrium, the ultimate rest. That rest is not nothing. It is something, even if the something is the most minimal something that physics allows. It is the quantum vacuum, humming at its lowest energy. It is the background of cosmic photons, stretched to wavelengths that approach the size of the observable universe. It is the faint possibility of fluctuations, of the occasional random arrangement of particles that briefly deviates from perfect uniformity before returning to it. It is the universe at its most fundamental, stripped of everything transient and complicated and energetic, left with only what the laws of physics will not allow it to give up. That is the destination. Not darkness in the sense of nothingness, but darkness in the sense of rest. The universe, after its long and luminous and finally quiet journey, lying still at last. Throughout tonight's journey, we have been encountering numbers that resist ordinary comprehension. We began with 100 trillion years, the rough span of the Stelliferous Era, which already exceeds the current age of the universe by a factor of about 7,000. Then we moved to the Degenerate Era, unfolding over timescales of quadrillions and quintillions of years. Then to proton decay, operating on timescales of 10 to the 40th power years. Then to the evaporation times of stellar mass black holes at 10 to the 74th power years, and supermassive black holes at 10 to the 96th power years or beyond. And then, without any clear ceiling, to the dark era, which may stretch for longer still, potentially forever. These numbers are not decorative. They are not chosen for dramatic effect. They are the actual outputs of physics calculations, derived from the same equations that predict the behavior of atoms in a laboratory and the motion of planets in the solar system. They are as real and as honest as any number in science. But they are also, without any doubt, beyond what the human mind can directly feel. We can write them. We can manipulate them mathematically. We can compare them to one another and note that some are larger and some are smaller. But we cannot feel them the way we feel the difference between an hour and a day, or even between a year and a century. This limitation is worth sitting with for a moment, because it is one of the most interesting things about thinking deeply about the future of the universe. We have built a science capable of describing things so far beyond human experience that the descriptions themselves become a kind of poetry, a language of numbers that points toward realities the imagination can gesture at but never fully grasp. And there is something humbling about that, something that invites a particular kind of intellectual honesty, an acknowledgement that knowing and feeling are not the same thing, and that the universe does not owe us the comfort of scales we can experience. One way to approach the incomprehensibility of deep time is through analogy, through the construction of comparisons that at least gesture in the right direction, even if they cannot fully bridge the gap. We have already used some of these. The comparison of the Stelliferous Era to a single day in which all of human history occupies the first second. The comparison of the proton decay timescale to a duration so long that writing the current age of the universe as a number of years, and then comparing it to the proton decay timescale, is like comparing a single atom to the observable universe. These analogies do not solve the problem of comprehension, but they orient the mind, give it a direction to look, provide at least a rough map of the territory, even if the territory itself remains unexplorable. Another approach is to simply practice sitting with the numbers without trying to convert them into something familiar. 10 to the 100th power years. Let that number exist in your mind without trying to visualize it as a pile of years or a string of days. Just let the notation stand. Let the exponent of 100 carry its own weight. Let the vastness of it be a fact that you hold lightly without gripping. The universe does not require you to fully comprehend its timescales in order for you to appreciate the story they tell. The story is coherent and beautiful even if certain chapters are written in a language of numbers that exceed direct experience. There is a mathematical notation that helps physicists work with these numbers without being overwhelmed by them. It is called scientific notation, or sometimes power of 10 notation, and it represents large numbers as a coefficient multiplied by 10 raised to some power. The number 1,000,000, which is a 1 followed by 6 zeros, is written as 10 to the 6th power. The number 1,000,000,000 is 10 to the 9th power. The current age of the universe in years is approximately 10 to the 10th power. The proton decay timescale is 10 to the 40th power. The evaporation time of a large black hole is 10 to the 96th power or beyond. Each step up in the exponent represents a factor of 10 increase in the number, and the exponents we have been dealing with in the black hole era and beyond represent numbers so large that if you wrote them out fully, the trailing zeros would fill many pages. But even scientific notation reaches its limits as a tool for conveying meaning when the exponents themselves become very large. 10 to the 100th power is already a number with 100 zeros. 10 to the 1,000th power has 1,000 zeros. And some of the timescales that cosmologists have calculated for processes in the very far future involve exponents that are themselves expressed as powers of 10, creating what are sometimes called googolplex scale numbers. Numbers so large that writing them out would require more space than the observable universe contains. At these scales, the very concept of a specific number begins to feel less meaningful than the concept of an order of magnitude. Whether a particular process takes 10 to the 100th power years or 10 to the 101st power years matters very little in the grand scheme of things. Both represent durations so far beyond any practical reference that the difference between them is itself incomprehensible. What matters is the sequence, the ordering, the fact that this process happens before that one and after this other one, that the universe passes through its eras in a specific order determined by the specific magnitudes of the timescales involved. This emphasis on sequence over precise number is actually a very natural way to think about deep time, and it reflects how cosmologists themselves often approach these discussions. The precise evaporation time of a specific supermassive black hole is less important than the fact that supermassive black holes evaporate after stellar mass black holes, which evaporate after neutron stars decay through proton decay, which happens after white dwarfs cool, which happens after red dwarfs exhaust their fuel. The order tells the story. The specific numbers are the supporting cast. There is also something liberating about accepting that these timescales cannot be felt directly. It removes the pressure to comprehend them fully and replaces it with a different kind of engagement, something closer to wonder than to understanding. When you encounter a number like 10 to the 96th power years, the appropriate response is not to strain for a mental image of that duration, because no such image is possible. The appropriate response is something quieter and more open, a recognition that the universe operates on scales that dwarf the human mind not by a little, but by so much that the comparison itself becomes a kind of meditation on the limits of experience. The universe does not care whether we can comprehend it. It will unfold across its deep timescales, whether or not any conscious being is present to observe it, whether or not any mind is capable of holding its full extent in awareness. The black holes will evaporate. The degenerate era will give way to the black hole era. The dark era will stretch forward for what may be an eternity. All of this will happen not because anyone understands it, but because the laws of physics are what they are and time is what it is, and entropy always increases. Our role in this story is not to comprehend it fully. Our role is to be present to the part of it we inhabit, to appreciate the extraordinary circumstances of the Stelliferous Era, to feel the richness of a universe still full of burning stars, and to let the knowledge of the deep future provide the perspective that comes from understanding one's place in an enormous story. We are not here to hold the whole story in our heads. We are here to be genuinely alive in our chapter of it, and to be grateful that our chapter, with all its light and warmth and complexity, is the one we were given. The numbers beyond imagination are not obstacles to understanding. They are invitations to a different kind of understanding, one that does not demand direct experience but accepts the testimony of calculation, one that does not require comprehension to allow appreciation, one that finds meaning not in the ability to feel every number, but in the ability to follow the direction they point. They point toward a universe that is patient, vast, and in some deep sense, at peace with its own eventual stillness. And that direction, even if we cannot follow it all the way to its end, is worth knowing. One of the most striking things about the long future of the universe, taken as a whole, as a single arc of change from the present moment to the dark era, is its directionality. It moves, always and without exception, in the direction of greater quiet. Not in the sense that sound grows less, because space has always been silent and will always be silent in the acoustic sense, but in a deeper and more meaningful sense, in the sense that activity decreases, that energy exchange slows, that the processes by which the universe does things become less frequent and less energetic as time goes on. The universe grows quieter with age, and following that quieting, era by era, is one of the most profound and most meditative experiences that cosmological thinking can offer. In the Stelliferous Era, the universe is extraordinarily noisy by physical standards. Not audibly, of course, but energetically. Stars are exploding in supernovae, releasing in a single event more energy than the sun will produce in its entire 10 billion-year lifetime. Galaxies are colliding, their gas clouds compressed by the interaction into new rounds of star formation, their structure disrupted and reformed over billions of years of gravitational interaction. Quasars are blazing at the centers of young galaxies, their central black holes consuming gas at rates that produce luminosities 1 trillion times that of the sun, outshining entire galaxies of hundreds of billions of stars. The universe is, energetically speaking, a very active place. Even in the more settled middle period of the Stelliferous Era, the period we currently inhabit, the level of activity is extraordinary. The sun produces 4 times 10 to the 26th power watts of energy, continuously, every second. The Milky Way contains hundreds of billions of similar stars, each producing comparable amounts of energy. The observable universe contains 2 trillion galaxies. Multiply these numbers together, and you get a total luminosity of the observable universe that is a number so large it has no convenient name. This is the energetic background noise of the Stelliferous Era, the constant roar of nuclear fusion happening simultaneously in countless stellar cores across the cosmos. Now follow this forward in time. As the Stelliferous Era progresses, the most energetic events become less frequent. The rate of supernovae declines as the rate of star formation declines. The quasars fall quiet as the gas supply that fuels them is exhausted. The galactic collisions become less frequent as the local group merges into a single structure, and the other galaxy groups recede beyond any possibility of interaction. The average luminosity of the universe falls, decade by decade, millennium by millennium, era by era. By the time the red dwarfs dominate the late Stelliferous Era, the universe will be a much quieter place energetically. Red dwarfs produce only a fraction of a percent of the sun's luminosity. A universe populated primarily by red dwarfs is a dim universe, a universe whose total energy output is a small fraction of what it is today. Still active, still producing light and heat, still capable in principle of warming planets and supporting chemistry. But noticeably quieter than the universe we currently inhabit. Then comes the transition to the Degenerate Era, and the quieting becomes much more pronounced. The last stars go out. The nuclear fires that have been the primary energy source of the cosmos for 100 trillion years are extinguished. What remains are white dwarfs, slowly cooling, and neutron stars, slowly spinning down. The total energy output of the universe drops by an enormous factor at this transition, from the combined luminosity of the last red dwarfs to the faint thermal radiation of cooling stellar remnants. The universe at the beginning of the Degenerate Era is dramatically quieter than the universe at the end of the Stelliferous Era, which was itself much quieter than the universe of the present day. As the Degenerate Era progresses, the quieting continues. White dwarfs cool from thousands of Kelvin to hundreds to tens. Their thermal radiation, already faint, becomes fainter still. Neutron stars spin down and their pulsing signals fade. The occasional merger or rare event punctuates the silence, but these events grow rarer as the era extends. The universe settles into a deep, cold, nearly uniform quiet that is broken only by the exceptionally rare collision or accretion event, and even those become less frequent as the Degenerate Era extends over timescales of quadrillions of years. The black hole era is quieter still. Black holes are, by definition, the darkest objects in the universe. They absorb radiation and emit only the faintest possible Hawking radiation, so faint that in the early black hole era it is completely swamped by the cosmic background temperature. The universe in the black hole era is darker than any state it has previously been in, darker even than the late Degenerate Era, because the white dwarfs that still faintly glowed in that era are now gone, dissolved by proton decay into the background photon sea. What remains is the nearest thing to perfect darkness that physics allows, broken only by the theoretical Hawking glow of black holes too faint to detect at any practical distance. And then comes the dark era, and the quieting reaches its ultimate expression. The black holes are gone. The last Hawking radiation has spread into the void. What remains is the near-perfect stillness of a universe in approximate thermal equilibrium, a sea of particles and photons so evenly distributed and so low in energy that the distinction between signal and background disappears entirely. The universe has become, as nearly as physics allows, silent. This progression, this long, slow quieting across eras and timescales, is not simply a physical process. It is also a kind of story, a narrative with a character arc, and the character is the universe itself. The universe begins its life after the Big Bang in a state of concentrated, explosive, creative energy. It burns through that energy over trillions of years, converting it from organized, low-entropy forms into diffuse, high-entropy forms. And as it does, it produces, almost as a byproduct, the complexity and richness and warmth that make galaxies and stars and planets and life possible. The quieting of the universe is inseparable from the flourishing of the universe. The same process that is slowly moving the cosmos toward heat death is the process that, in its earlier and more concentrated stages, produced everything that has ever existed. The philosopher might say that the universe spends its energy on the way to silence, and what it spends it on is everything. Every star, every world, every living thing, every thought that has ever occurred in the mind of any conscious being anywhere in the cosmos, all of it is a product of the universe spending down its initial stock of low entropy on the long journey toward equilibrium. The richness of the current universe is not in spite of the second law of thermodynamics. It is because of it. It is what the second law looks like in the middle of its long journey, when there is still energy to spend and gradients to drive processes and complexity to emerge from the flow. To watch the universe grow quieter, era by era, is to watch that energy being spent. And there is something deeply moving about this, something that connects the abstract physics of entropy to the lived experience of being alive in the middle of it. Every moment of warmth, every photon of sunlight on a face, every flicker of a candle, every crackling fire, every storm and every wave and every living heartbeat is the universe spending its energy, moving toward quiet in the most extravagant and beautiful and temporary way imaginable. The quiet at the end is not a punishment or a loss. It is simply what comes after the spending is done. And the spending, the long, luminous, energetic era of stars and life and complexity, is the point. That is the part of the story that has meaning. That is the chapter that matters. The silence that follows is not the meaning. The noise was the meaning. And we are here right now in the noise. We have traveled a very long way tonight. We have followed the universe from where it stands now, blazing with the light of 2 trillion galaxies and their countless stars, through the slow decline of the Stelliferous Era, through the long cooling darkness of the Degenerate Era, through the patient evaporation of black holes across timescales with dozens or hundreds of digits, through the near-perfect stillness of the Dark Era. We have looked at the universe from the vantage point of its very end, or as near to its end as physics currently allows us to see. And now, having made that journey, it is worth asking the question that gives the whole trip its meaning. What does this mean for us, the people who are here right now, in the early morning of the Stelliferous Era, alive in the most luminous and energetic chapter of the entire cosmic story? The first thing it means is perspective. And perspective, properly experienced, is one of the most valuable things that thinking can give us. Not perspective in the diluted sense of being reminded that things could be worse, but perspective in the deeper sense of understanding one's actual place in a much larger story. We live in a universe that is 13.8 billion years old. That sounds ancient. But we have now seen that the universe as it currently exists, full of burning stars and active galaxies and warm planets, is in the early stages of a story that will last for time so long that our current era does not even constitute a noticeable fraction of the whole. We are not in the middle of the story. We are in the very first pages. We are in the universe's childhood, its most energetic and most creative time, and we are fortunate enough to be alive in it. This perspective does something interesting to the anxieties of daily life. It does not eliminate them. The concerns and pressures and difficulties of a human life are real, and their reality does not diminish because the universe will be around for a long time after we are gone. But perspective changes the emotional weight of those concerns. When you have just spent time genuinely thinking about the dark era, about the universe in the state it will eventually reach after the last black hole has evaporated, and the last particles are drifting alone through an expanding void, the ordinary anxieties of an ordinary life acquire a different flavor. They become more manageable, not because they are less real, but because they are placed in a context so vast that their urgency naturally softens. The physicist Richard Feynman once said that he found the contemplation of the immensity of the universe not terrifying but exhilarating. He found it interesting. There is a particular quality of intellectual peace that comes from engaging seriously with things much larger than yourself, from genuinely trying to comprehend scales and timescales that dwarf human experience, from following the logic of physics all the way to its most extreme conclusions. It is the peace of knowing your place, not in the diminishing sense of knowing your insignificance, but in the grounding sense of knowing where you are in a story much larger than yourself. The second thing the long future means for us is an appreciation of rarity. We have now seen that the conditions we take for granted, the existence of stars, the availability of warmth from a nearby sun, the chemistry enabled by stellar nucleosynthesis, the very atoms our bodies are made of, all of these are products of the Stelliferous Era, the age of stars. They are not permanent features of the universe. They are temporary, specific to this era, and they will not be available forever. The raw material for life, for planets, for warmth, for complexity of any kind, exists only while there are stars burning, and the stars will not burn forever. This does not mean that life is doomed in any near-term sense. The sun has 5 billion years of hydrogen fuel remaining. There are red dwarfs in our galaxy that will burn for trillions of years. The Stelliferous Era itself has 100 trillion years still ahead of it. These are timescales so vast that any practical concern about the end of the age of stars is not merely premature, but essentially meaningless on any human scale. But knowing that the era is finite, knowing that the conditions for life are specific to this chapter of the universe, deepens the appreciation of those conditions in the same way that knowing a season will end deepens the appreciation of it while it is present. The cherry blossoms are more beautiful because they fall. The summer is more vivid because it ends. And the Stelliferous Era, in the context of the universe's full timeline, is a brief and extraordinary blossoming, a finite period of warmth and light and chemical richness that will eventually pass, leaving behind the long, cold patience of the degenerate and black hole eras. To know this is to experience the present universe, even through all its problems and difficulties, with a kind of gratitude that is not available without the perspective of deep time. The third thing the long future means for us is a reframing of what matters. In the context of the universe's deep future, the things that seem most permanent and most solid in our daily lives turn out to be extraordinarily transient. Nations, civilizations, planets, even stars, are temporary on the timescales we have been discussing. The sun will exhaust its hydrogen in 5 billion years. The Milky Way will merge with Andromeda in 4 billion years. The last red dwarf will go dark in roughly 100 trillion years. Against the background of the dark era, even these enormous spans of time look brief. What endures, in the only sense that deep time allows for the concept of enduring, are physical laws. The second law of thermodynamics will operate in the dark era exactly as it operates today. The principles of quantum mechanics that govern Hawking radiation will be as valid in the black hole era as they are in a laboratory experiment conducted right now. The constants of nature, the speed of light, the strength of the gravitational constant, the mass of the electron, are expected to remain unchanged across all of these eras, providing the consistent physical framework within which the universe's long story unfolds. This constancy of physical law across deep time is itself one of the most remarkable and most underappreciated facts about the universe. We live in a cosmos governed by rules that do not change. The same physics that allowed the first stars to ignite allows the last black holes to evaporate. The same equations describe the behavior of a hydrogen atom in the early universe and a hydrogen atom in the late Degenerate Era. The universe is consistent across its entire history and its entire future, and that consistency is what makes it possible to describe the future at all. What makes tonight's journey a legitimate exercise in science rather than in pure speculation. The fourth thing the long future means for us is a kind of humility about our current understanding. The story we have been telling tonight is our best current understanding of the universe's future, derived from the best physics we currently have. But physics is not finished, and our understanding will change. We do not know whether proton decay occurs or not. We do not know the ultimate nature of dark energy and whether it will remain constant or change as the universe ages. We do not know the details of quantum gravity, which would be needed to describe what happens at the very end of black hole evaporation or at the singularity inside a black hole. We do not know whether the universe is truly infinite or merely very large. Each of these open questions could, if resolved differently, change the story of the deep future in significant ways. If dark energy changes over time, the expansion of the universe might not continue indefinitely. If quantum gravity reveals new physics at the Planck scale, the final evaporation of black holes might look different from what Hawking's calculation predicts. If the universe turns out to be truly infinite, the concepts of total entropy and heat death require rethinking. The story we have been telling is our best current answer to the question of what lies ahead, and like all of science's best current answers, it is provisional, subject to revision, and honestly uncertain in ways that we have tried to flag as we went. But the broad outlines, the overall arc from Stelliferous Era to Degenerate Era to Black Hole Era to Dark Era, the direction of increasing entropy, the eventual fate of matter and energy, these are robust enough that they are unlikely to be overturned entirely. They may be modified, details may change, but the universe will not suddenly be found to be permanent or to cycle back to its beginning. The direction of travel is clear, even if the exact path remains partly unknown. And that direction, that long, slow journey toward quiet, is not a counsel of despair. It is a fact about the universe that, properly understood, enriches rather than diminishes the present. We are here, in the loud and luminous beginning of the story. The silence is coming, but it is so far away that it belongs to a different kind of future than any human mind can practically encompass. For all purposes that matter to living beings, the fire is still burning, the stars are still shining, and the universe is still in the full energetic flush of its most creative era. That is where we are. That is the gift of the deep time perspective. Not the knowledge that everything will end, but the knowledge that right now, In this moment, in this era, we are living in the most remarkable and most improbable chapter of the entire cosmic story. We have been on a very long journey tonight, and now we have arrived somewhere quiet. Not at the dark era itself, not at the end of the story, but at a place inside the story where it becomes possible to simply rest with everything we have seen. To stop following the physics forward, and to simply be present with the knowledge we have gathered, letting it settle into the body and the breath the way that a long walk settles into tired and satisfied muscles. The long future of the universe is not easy to hold in the mind. We have said this before, and it remains true even after everything we have discussed. But there is a difference between holding something and resting with it. Holding something requires effort, requires the continuous work of keeping it in focus, of not letting it slip. Resting with something is different. It asks less and gives more. It asks only that you be present, that you let the knowledge be what it is without trying to grasp it completely, that you allow the scale of what you have heard to exist around you without needing to reduce it to something manageable. So let us rest for a moment beneath the deep time of the universe. Not beneath the dark era, not beneath the silence of the last evaporated black hole, but beneath the awareness that these things exist, that the universe has this kind of future, that the story we are part of is longer and stranger and more patient than any version of it that daily life could suggest. Begin with your breath. It is happening right now. This simple, automatic, ancient process of drawing air into the lungs and releasing it again. The oxygen you are breathing was forged inside a star that died long before the sun was born, scattered through space by a supernova explosion, incorporated into the gas cloud that eventually became the solar system, dissolved into the early oceans of the Earth, produced by the photosynthesis of countless plants over billions of years, and now it is entering your body. You are, in the most literal possible sense, breathing the products of the Stelliferous Era. The Stelliferous Era is not abstract or distant. It is in your lungs right now. The carbon in your body, the calcium in your bones, the iron in your blood, all of it has the same history. All of it was forged in stellar interiors and scattered through space by stellar deaths. You are a temporary arrangement of stellar ash, animated by the ongoing energy of a nearby star, existing in the narrow habitable zone around that star during the brief period when the conditions for your kind of complexity are possible. You are, in a very precise sense, a product of the Stelliferous Era, and you could not exist in any other era of the universe's history. The Degenerate Era could not produce you. The cooling white dwarfs could not provide the chemistry or the warmth or the energy gradients that life requires. The black hole era could not produce you. The dark era certainly could not. Only the Stelliferous Era, with its burning stars and warm planets and rich chemistry, could give rise to the kind of complexity that produces conscious beings who can look up at the sky and wonder what lies ahead. You are the universe knowing itself in the form that is only possible in this era. You are a temporary configuration of matter that has organized itself into something aware enough to ask questions about the long future, sensitive enough to feel the weight of deep time, imaginative enough to follow the physics all the way to the last evaporating black hole, and then come back to breathe the night air of the Stelliferous Era, and find it more precious for having made that journey. Resting beneath deep time means allowing this to be true without needing to do anything about it. The universe is going to move through its eras regardless of whether any conscious being comprehends them. The second law of thermodynamics will continue to operate. The black holes will eventually evaporate. The dark era will eventually arrive, or the closest thing to it that physics allows. None of this depends on your understanding or your approval or your presence. It will happen in the slow, patient, indifferent way that the laws of physics execute themselves across timescales that dwarf any possible observation. And you are here, in the middle of it, in the most extraordinary chapter of it. And that is enough. That is more than enough. That is, in fact, everything that a conscious being in the Stelliferous Era could possibly ask for. Resting beneath deep time also means releasing the urgency that modern life tends to generate. The urgency of schedules and deadlines and obligations, the feeling that there is not enough time, that things need to happen now and not later, that the present moment is somehow running out. This feeling, which is so common and so exhausting, rests on a particular relationship with time, a relationship in which time is scarce, and therefore precious and therefore anxiety-inducing. But the perspective of deep time replaces scarcity with abundance. Time is not running out. Time is, in the context of the universe's full story, almost impossibly abundant. The universe is barely started. The Stelliferous Era has 100 trillion years remaining. The story is long and slow and patient in ways that daily life never is. This does not mean that your time does not matter. Your time matters enormously, precisely because it is finite in the way that the universe is not. The contrast is part of the point. The universe will go on, you will not. And that finiteness is not a tragedy. It is the thing that makes your experience of the Stelliferous Era unique and irreplaceable. You are here now. The stars are there now. The warmth of the sun is available now, and the complexity and beauty of the living world is present now, and the capacity to think and feel and wonder is available to you now. These things will not always be available, not because the universe will end, but because you are a creature of a particular moment, and your particular moment is now. So rest here in the now, with the knowledge of what lies ahead but without the weight of it. The Degenerate Era is far away. The black hole era is incomprehensibly far away. The dark era is further still. What is close, what is real, what is present, is this moment, this breath, this awareness, this sky full of stars that are each a burning reminder that we live in the most luminous era the universe will ever know. The stars above you, if you can imagine them or if you can see them, are not old news or background decoration. They are active expressions of the Stelliferous Era, of the age that gave rise to everything you are made of and everything you can experience. Each one is a nuclear furnace that has been burning for billions of years and will burn for billions more. Each one is a sun, with its own light and its own warmth and its own possibility of worlds. And there are hundreds of billions of them in the Milky Way alone, and 2 trillion galaxies of similar abundance spread across the observable universe, all of them burning right now. All of them adding their light to the cosmic total that makes this era, by the standards of what will come after it, an age of extraordinary and temporary and precious luminosity. Rest beneath that. Let the knowledge of deep time, of the long future, of the slow quieting of the universe across unimaginable timescales, be not a weight but a frame that makes the picture it surrounds more vivid, more precious, more fully seen. The picture is this moment. The frame is everything we have discussed tonight, and together they make something complete. You are in the Stelliferous Era. The fire is burning. The stars are there, and you are awake enough to know it.